Hi everyone, and welcome to Building Games with SFML. In this video course, which is going to last roughly 2 hours in all, we'll be learning SFML by building a simple game in C++. Everyone has a different background. Some of you are novice, others experts, and thus, you all have different expectations from these videos. That's why this first video, labeled Course Overview, will introduce what we will be doing. Along the way, I will also answer questions like, who does this course target? What knowledge do you need to follow this course? And so on. So this is going to be a course for people who can write in C++, given that SFML is a C++ library. If for some reason you don't use C++, there are various bindings bought by the SFML community that makes SFML available in other programming languages. If you aren't afraid to try these bindings, just go ahead with this course, because the concepts are the same in any language. We actually don't expect you to know anything about SFML. You'll be introduced to the whole framework, module by module, in the first 2 sections, and this is going to occupy a third of the total course. Again, for people who won't use C++, the concepts are the same, but with minor differences due to programming language differences. For those who have an experience using SFML but don't have much experience in building games in general, this course will also provide you with design patterns applied to games and show you how to write games efficiently. At the end, even if you are not proficient in many of these 3 areas, don't worry, because this course was prepared from the ground up to get you started with building video games using SFML. Well, it's not an accident that you're here, and I assume you already know a couple of things about SFML. Since this is the start of a long series of videos, perhaps we should better make things clear from the start on what SFML is and what SFML is not. SFML is a C++ library and is similar in nature to the SDL library if you have any experience with that library. The biggest difference is that SFML is a C++, while SDL is C. Like stated before, if you're more comfortable with other programming languages and wish to program SFML games using your favorite language, there's a high chance that SFML has a binding for it. Over the years, the community has created various bindings for program languages like Java, Python, C#, Ruby, and various others. SFML is a low-level framework giving us simple and fast access to various components of your computer, like the audio and the graphics. It's probably best for building 2D games, even though 3D games are doable too. SFML isn't a GUI library at all, and except creating windows to contain the graphics of your game, it doesn't offer any dialog boxes, buttons, or whatsoever. SFML is a cross-platform. It allows one code base to compile and run on many operating systems. As for SFML 2.3, it supports Windows, Mac OS X, Linux, and has an experimental port for Android and iOS. That's good news, as our end result game is going to run on all these platforms. Exciting, isn't it? I would like to end this course overview by showing you in which environment we'll be working. I will also quickly talk about the IDE we will be using. As most of you will recognize, I'm on Ubuntu, and this is the chosen operating system. Although I'm targeting a novice and intermediate audience, you might be surprised by this choice. So let me explain the reasons behind it. First, Ubuntu is one of the distributions of Linux, among others. While Linux is reputed to be complicated, which might be true when we grew with Windows, developers of Ubuntu have put a lot of effort to make the transition easy. Here, I'm using version 14.04 of Ubuntu. The reason behind that choice is using, and mastering Linux is an important key in every programmer's career. If you wish to be a true game programmer, you'll always deal with Unix-based systems involving consoles and all these scary things. This is because most of the things in a computer originate from it. By the way, Mac OS X is also a Unix-based system, so you'll be fine with it too. That said, feel free to use any operating system you want because except this section, The rest of the tutorial still applies to other environments. I'd like to make a quick note for people who will choose Ubuntu. This is about the graphics driver support. Without digging into details now, SFML is going to exploit the capabilities of your computer, and if you have a graphics card, it's going to use it. That's why you need to have your graphics drivers properly installed. On Ubuntu, we have the free and generic graphics driver by default. But if ever they fail to run properly, Ubuntu makes it convenient to switch to the proprietary ones. You can go to the System Settings, click on Software and Updates, and there's a tab on the right, Additional Drivers, where you can conveniently switch. That's it, because installing a graphics card isn't the scope of this tutorial. Now I will show you the resulting game. This is going to be a Pac-Man clone I named Pac-Woman. This is nothing more than a regular Pac-Man clone, but with different visuals and a couple of modern features to make it less of a boring exact same clone. If you already got your hands dirty and tried to build other games before, you might think that writing a Pac-Man-like game is too simple or not fun. I could agree with you, because I'd myself be more excited to write a platform like Rayman, enhanced by some modern features like a light system with a whole physics engine, and certainly with much more appealing assets than that. However, I'd like to point out that even simple games like Tetris or Arkanoid can be more challenging than you think. Let's start the game by inserting a coin. For instance, look at how the enemies are trying to catch me. To implement that requires writing artificial intelligence algorithms. Also, you can notice that the entities running through the maze are animated, which requires us to set up a timer and alternate the images drawn on the screen using an animator. Look at how curvy the walls of the maze are. We'll be using some advanced techniques to achieve this result. Finally, let me finish that level. First, because I also want to show you the camera tracking system we're going to implement. Here we are. We can also play Pac-Man on a very large maze using a camera. So, even though the game is a simple Pac-Man clone, there are quite a lot of stuff to implement, and believe me, when it comes to game programming, always start with simple projects before starting to work on a larger undertaking. Before I leave you and see you in the next video, I have to introduce the code editor I'll be using to write this game. This is Genie, the program in front of you. Although it isn't very popular, this is an awesome IDE I had the chance to discover and work with for years. Genie is simple, but not the most convenient editor. It supports many programming languages and provides syntax coloration for these languages. It also comes with an embedded console, which is really essential to me. These are two strong points of why Genie is my IDE default of choice for cross-language and cross-platform projects. In fact, I mainly chose Genie because this course is geared towards Linux and its console. I want to show you how mastering the console can be a huge advantage and a tad more convenient. Later, you'll more easily move to another IDE, perhaps more appealing, or which automates tasks. But in the meantime, you've got to understand what happens under the hood to better use other IDE, and Genie is the perfect choice for that. So if you want to install Genie, you can get it via the Ubuntu Software Center or by downloading the installer on the official website. Of course, feel free to pick up the one you like because it's most important that you're comfortable using it. But don't forget, you'll be compiling, testing, and debugging a lot, so the IDE has to make it convenient. With the embedded console you can see at the bottom, we will easily compile and recompile the code, inspect the result, and various other useful things. I'll explain it to you in much detail in the next set of videos. Some other IDEs I recommend are CodeBlocks and Qt Creator. These are two very good IDEs, but feel free to research and discover yourself. That's it. Now that we know where we're going, it's time to step forward and start our long journey together with our next video, which is about installing SFML. I wish you a happy viewing and hope you'll enjoy these videos to all its extent. Welcome to the very first section. There's a lot of content to cover, from installing SFML and discovering its modules, to designing and writing the game itself. That's why this course is organized into sections, and the very first one is Getting Started. In Section 1, we're going to take a look at compiling and installing SFML first. Then we'll look at creating and setting up a project. And lastly, we'll anticipate the publishing step of our game and see how to deploy it intelligently. Unfortunately, these three topics are tightly related to the operating system you choose to develop, and in this course, they will only be covered by Ubuntu. If you use Mac OS X, you'll be happy because most of the steps look alike. However, for Windows users, you'll probably need an additional tutorial that you can find on the SFML website. Don't worry, the other sections are not specific to Ubuntu. The first step in using SFML is installing it. So let's see how to do that. Here is a brief overview of what is covered in this video. As you can read, we'll install SFML from command line, then see how to compile it ourselves so we can benefit from the latest changes. At the end, we'll have a look at CMake software, which allows us to cross-compile and cross-publish programs in no time. To install SFML on Ubuntu, you simply fire up a console and type sudo apt-get install lib sfml-dev. Enter your password, and it will now download SFML and install the requested package. This is as simple as that, because Ubuntu maintains its own library of virus-free software. This is actually just what we need to develop the game in this tutorial. However, SFML is a community project always under active development. New features are added frequently, and sometimes bugs are corrected. When you want the benefits of these daily updates, you can either wait until the next major release, which occurs averagely every 5 months, or you can compile the latest source code. You might be interested in compiling the latest source code of SFML, so instead of contenting ourselves with the easy way, I will use this opportunity to show you how we can compile SFML. We will start with undoing the installation of the SFML package by typing sudo apt-get purge lib sfml-dev. Like you can see, installing and removing programs on Ubuntu is a very easy process. The first step is to obtain a copy of the latest source code. We must browse the official SFML website for that. Once on the page, we need to get to the Download section. Then, click on Git Repository button, which links us to GitHub, the website where the SFML source code is maintained. On the right, find the Download Zip button to download and archive with the current code. While it's downloading, I will cover CMake, the software that will allow us to compile both SFML and our game later. CMake is a powerful cross-platform solution to compile and install cross-platform programs or libraries like SFML. So, why do we need CMake? Each targeted operating system functions way differently, and it would be tedious to set up a whole IDE with their compilers, which aren't the same across operating systems, by the way, every single time we want to compile, install libraries, or distribute applications. It involves a lot of manual steps and downloads from every side. On top of that, we're not safe from a bad manipulation. The solution to this problem is CMake, a tool to cross-compile and cross-install software. We'll use this very same software to compile our game in the next video, so listen carefully. To install CMake, it's not harder than how we installed SFML earlier. Fire up a console and type sudo apt-get install CMake. CMake also comes with a GUI front-end, which is a program allowing you to use CMake without using the console. However, using the console is much more convenient and you'll gain speed. Speaking of console, I will make a small parenthesis for Linux newbies about how to use the console a little and give a tip to organize your files. When we open a console, we are in the home directory. you type ls to list files and directories. We can read videos, music, pictures, etc. At the same time, I will open the File System Manager and show this very directory. So this is the home directory, and we can see the exact same files, videos, pictures. Now I will create a directory in the home directory named Workspace, but I will do that from the console. I type mkdir, that stands for Make Directory, and then the name of the directory Workspace. Now if I rerun the ls command, I should see the new directory. And we can see it gets reflected in the File System Manager as well. Well, I advise you to place everything related to programming in this directory, your projects, the third-party libraries you compile at hand, etc. But this is just an organization tip, and it's up to you to follow it or not. There's nothing really astonishing yet about the console, but this gives you the ability to automate the creation of directories, and later, we'll be able to quickly compile games and change the compilation options. Let's check if SFML is downloaded. Hopefully it is, and we have to extract the content of the just downloaded archive. And we will extract it in the just created Workspace directory in a subdirectory named SFML. Before we move on with the compilation, let's make sure files were properly extracted where we expected them. Let me open the File System Manager and browse the folder manually. Apparently, everything is in order, so let's proceed with the compilation of SFML. Again, I will use a console. With the command line cd workspace/sfml, I move myself from the current directory to the SFML source directory. I can even verify it with the ls command. Now prepare to be amazed. Compiling is the result of two command lines. The first is CMake. It reads the configuration file and generates the build files according to the underlying platform, which in our case is Linux. If nothing goes wrong, it has transformed the source code into a compilable state. The next command line is make, which performs the compilation. SFML is now compiling. Like you can notice, it takes quite a lot of time. If you have a closer look to the console, you can see it builds each source file one by one, and also module after module. You can see module graphics is being compiled. While SFML is compiling, I have to explain that to perform these steps, you actually need to install a bunch of packages that SFML depends on. You can get a list of these packages on the SFML website, and you would install them by typing something like sudo apt-get install package 1, package 2. Unfortunately, there's not enough time to take a coffee break because compiling SFML is already done. The last command we'll need is sudo make install. This is to install SFML on the system. Basically, this will install the headers and the resulting libraries in /usr/local, which is the standard location on Linux. We are now surprisingly done with compiling and installing SFML. In a few minutes, we built SFML and installed it. The same step could have taken forever if we were to install an IDE, set up the SFML source code, and all these things ourselves. I hope you enjoyed how simple and fast compiling SFML is. In this video, we learned that CMake is a powerful tool to cross-compile libraries and application. Incidentally, we will use it in our game project. With SFML installed, we can jump to the next video, which is about setting up our game project. We will understand that the overall process will be the same to compile our own game. Compiling will be as easy as typing the word make in a console. See you shortly. In the previous video, we covered the compilation of the latest source code of SFML using CMake. This video will teach you how to set up a command line project compiled by CMake. In this video, besides creating the command line project, we'll see good practices and tips to organize the project without wasting any time. We will also write a minimal CMake script, which is necessary to get one project compiled by CMake. Back on Genie, the IDE I briefly spoke about in the first video. This is where I'm going to write down the code of our game. But what name shall we give to our game? We could simply name it Pac-Man and use the original graphics to clone exactly the Pac-Man game released in 1980. But how would it be fun? Instead, we will name it Pac-Woman, and we'll replace the images to display a female version of Pac-Man. Let me start with making an important point. One project is equal to one directory. I'm stressing this point because a badly managed project results in a huge amount of wasted time. I myself went through it. Everything related to one project should be self-contained in a single directory. Source code, scripts to build the source code, images, sound files, documentation, notes, anything. Redistributing the project will be simply a copy of that directory. Let's create our project directory in the Workspace directory. We'll name it Pac-Woman. Inside it, we will gather all the files related to the development of this video game. Now, where should we place the source code? Well, it's up to you, but there are standard and typical layouts widely used that I highly recommend you should follow. Generally, simply place all your source files in a directory named src. In this directory, we will find the main file, main.cpp. For now, I will simply fill this source file with the main function and perhaps output Hello Pac-Woman. Let's go back to the root of our project directory. We also typically find two files here, which are readme.txt and license.txt. The README file generally contains basic information about the project as well as how to compile it. Let's quickly write it. Firstly, a title, Pac-Woman. Then a description. Control Pac-Man's wife in a gigantic maze. I will follow it with the authors section, Jonathan, and terminate it with a How to Compile section. Use CMake. It's easy. Here we go. Next is the license file, which contains the legal text that protects your work. We won't be using any license for our project since it comes with this tutorial. Actually, the code we see here is absolutely free. Thus, let's open that file and write, do whatever you want with the project files. For your project, I wouldn't advise such a permissive license. It would be just giving your work away. Instead, you could use the GPL license or any other one. Additionally, you could even find a file named contributors.txt, which lists all the people who contributed to your project. Anyway, I'll stop now because those are just basic tips to organize your source code. An exhaustive explanation on the matter is beyond the scope of these video tutorials. However, what is within the scope of these video tutorials is how to compile one game using CMake. CMake relies on a script which must be precisely named CMakeLists.txt. Be careful because the case counts. As such, the capital letters like M and C cannot be written in lowercase. We'll leave it in the root. The script must contain all the information telling CMake how to put the source files together to result in an executable. For instance, where to find the source files, what name to give the executable, the compiler options, or even what files to install when one wants to install the game. Open this weird-looking CMake script with your favorite text editor. The content of this file is written using the CMake language, a scripting language. I don't advise you to pay much attention to what I just copy and pasted here, the syntax or anything. Just remember what these lines do, and you'll be able to modify it according to your needs. Let's quickly go through it and try to understand the code line by line. The first line is self-explanatory. It prevents the script from being interpreted by CMake version below 2.6. The second line defines the project name. The third line enables the modern version of C++. It passes an additional flag to the compiler being std equals C++11. The line below defines a variable named src That stands for source and is a list of all source files to compile and assemble in order to generate the executable. So far, we only have the main file, main.cpp. This variable is then passed to the line below, which instructs CMake to create an executable out of this list of source files. The last 5 lines tell CMake to link against the 5 modules of SFML. We can now close the CMake file because we were done writing it. Our project is set up and ready to be compiled with CMake. To build the project, you would just proceed like you compiled SFML by running command CMake, then make. However, we will make one small exception because we will be intensively working in directory. Anytime you type CMake, you transform the whole project into a compilable state, adding dozens of files specific to your environment, which is not suitable when it comes to redistribute the project. Do you remember that redistributing a project should be just a copy-paste of the project directory? Well, if your directory is polluted by many files that are only specific to your environment, you would have failed to keep your project clean, and you cannot send it across to a friend. So instead, we'll create a subdirectory named build and go inside to platform the building tasks. Then, exactly like before, we'll type CMake, but this time we'll add 2 dots, meaning go search our CMake build script in the parent directory. Now we can compile the project using the make command as usual. Let's open the file manager and see what are the benefits of these extra steps. I'm inside the project directory, and I can notice the build directory where we just did the compilation. Other than that, the state of our project directory remained exactly the same. Nothing changed. Nothing is polluted with extra files except in the build directory, where we can see that a couple of obscure files have been created. When you want to redistribute your project, you would just delete the build directory. Inside the build directory was created the game executable, which is that file packwoman. I can launch the game by typing /packwoman. Right now it does nothing. Anyway, in this video, we have learned how to create a command line project. The key points to take away from this video are: be organized when it comes to managing the project, and simply type make anytime you make changes to get the result. In this section, we've taken an overview of the entire course, installed the SFML library, and taken a look at how to set up your project along with important notes on good practices. In the next section, we will investigate the SFML API and play a bit with the different modules present in the library. Welcome back. This is Section 2. The previous section was about setting up the project, and I hope you are setting up yours successfully. Otherwise, you won't be able to investigate the SFML framework with me. This section is all about investigating SFML to understand its main features. If something went wrong during the installation of SFML, don't give up. Take your time. Rewatch the previous videos, because it's often a matter of detail. If ever you cannot get SFML working, don't hesitate to ask questions on the SFML forum. We'll be happy to help you. I decided to dedicate an entire section to understanding the structure of SFML for those who aren't acquainted with the framework yet. Even if you already are a bit familiar with the 5 modules, this is a good opportunity for you to refresh your memory. The SFML framework isn't huge in itself. This is only 5 modules together. In this course, we're going to take a look at 4 of them. Network module won't be covered in this course. Networking a game is a tough topic, and we won't use it in our game. However, we still have a large set of features to cover in these 4 modules. That's why this section is going to be pretty big. So let's not waste a minute and get started. The name of each module can give you a rough idea of what they can be all about. Take the window module, for example. The word window makes us think this is about creating windows and manipulating them. The graphics module will certainly be about drawing graphics, possibly onto these windows. The audio module is definitely about playing sounds and music, and finally, the network module is about linking 2 computers over the network. But what could the system module be about? Indeed, the word system is of a large, broad term. So here is the answer. The system module provides cross-platform essential utilities to get our application portable. We can split this module in 4 parts. The first part is time. This module allows us to manipulate time because time is essential to games. It provides 2-dimensional vectors. In the game, we'll be dealing a lot with geometrical information, and vectors are useful for that. There's also strings. When working with text, we need to pay attention to encoding. One might use foreign characters such as Chinese characters or the Cyrillic alphabet. And the last part would be threads, which allows some code of the program to be executed at the same time. But this is a complex topic, and that's why we won't cover it in this video tutorial. This is where we reached the last time, the empty project of our game. We'll start playing a bit with each interesting feature of SFML now. Let's start with SFTime and SFClock, which are 2 classes that allow us to manipulate time in our game. Time is essential to games because without time, we wouldn't be able to animate entities on the screen. For example, if I decide that one monster takes 10 seconds to walk from the left side to the right side of the screen without being time aware, we cannot implement such a behavior. You'll be dealing a lot with time, and this is where these 2 classes come in handy. SFTime is a simple container that retains time. It can be 1 second, 2 seconds, or half a second. In fact, if we want to represent time in seconds, we could simply use a float type. I would write float time 1, and I would assign it a value like 2 for 2 seconds. Or I could change it to 1.2 to say 1 second and 200 milliseconds. But what if later, you or someone else uses another convention to represent time? For example, they use an integer to represent time in milliseconds. We would find ourselves with 2 variables of different types. This scenario is confusing and has a high potential of introducing bugs to the program. By dealing with 2 different conventions, we cannot easily add time to each other without going through a conversation step. In this case, I have to either multiply time 1 by 1000 or divide the time 2 by 1000. And on top of that, I also need to convert the type. To solve this problem, we use SFTime. It ensures no possible confusion and leaves less room for mistakes. To assign a given time, we have to use these self-explanatory functions. In fact, we also have microseconds. In time 3, I have put 1 second. Now we can conveniently do arithmetic operations. We can write time is equal to time 1 plus time 2 minus time 3. The internal representation of SFTime is irrelevant here. However, we can retrieve the time in seconds using asSeconds method. We can also get it in milliseconds. And in microseconds, I used auto to deduce the type, but actually, in seconds we get a floating point value. And for milliseconds and microseconds, we can use an integer. Now we can take the result of the above arithmetic operation and print it out. Remember, to compile, we simply have to type make. Now it's compiled, we can run the executable by typing // plus the name of the executable. We can see 3 values. The result of 1.2 plus 1.2 minus 1 second is equal to 1.4 seconds. The total values below are 1.4 seconds in milliseconds and microseconds. The next class we will investigate is the 2-dimensional vector. The usage of bracket with the float type inside should tell you it's a templated class. As such, I could have declared a 2-dimensional vector using an integer as well. A vector has 2 components, x and y, which are public attributes. That means I can access them directly with that syntax. Here we have assigned the value 4 to the x component and 2 to the y component. Later we can access these values. Now, what do we use vectors for? The word vector probably reminds you of math at school and the numerous properties that come with vectors. In SFML, this is exactly what Vector2 class models do. For instance, we can add another vector, or even multiply it with a scalar. Here, multiplying the value by -1, we can invert each value of the vector. If you remember even further, you will understand that a vector represents a direction with a magnitude. But actually, all this stuff might be far away behind you. However, this topic might be dull and not interesting, but you'll find out that this is really essential when it comes to games to be comfortable with manipulating geometrical information. For instance, experts compute and compare distance and angles in no time. They can tell whether two entities face each other by how much or how much distance one must travel to reach the other. At the beginning, this is a tiring process to compute all this information, but it becomes a natural process once you know vectors. Anyway, for now, just be aware that this class, SF Vector 2, can also be used to represent a two-dimensional position. Value 4,2 could say one entity is at cell 4,2 or pixel 4,2. But that's not all. Vectors could also be used to tell the size of a rectangle. This could be a rectangle with a width of 4 meters and a height of 2 meters. And we'll be frequently using vectors with the integer type or the float type. That's why SFML provides type def for them. Instead, you can write vector2i for integer, vector2u for unsigned integer, and vector2f for float. By the way, SFML also provides a three-dimensional vector. This vector works and behaves the same as vector 2, except that it has a third component, the z-value. Here we have assigned 8 to the z-value. For the last part of this video, we'll take a look at the SF string class from the system module. If you are familiar with the STL strings from the standard library, you'll understand it's about holding a piece of text, like this. SF string is exactly the same thing. We could simply replace std with sf, make the first letter a capital, and the code would still compile. It leads to a question. If the standard library provides everything we need to handle strings, why would SFML introduce such a class? The answer is, before C++11 kicked in, we couldn't handle strings in a portable way. Representing a piece of text is a delicate operation because it involves encoding, conversion, etc. If you've heard of ASCII, or UTF-8, or UTF-32, this is exactly about that. An encoding type enables us to encode a given piece of text efficiently according to the set of characters, resulting in different internal binary representation. For instance, think about Chinese characters or Western accents. SFML uses this string class to perform automatic conversation and ensure that the string representation is understood by SFML. But this is a complex topic, and we won't dig into it. However, practically all you need to know is, when using foreign characters in a text, like the Cyrillic alphabet or whatever, you have to add the capital letter L before the beginning of your string. To demonstrate, we will switch our keyboard to the Russian keyboard. I'm not a Russian speaker, but as far as I remember, the word yes in Russia is da. Without the L prefix, the code compiled, but the compiler interprets it as a string of char. However, we want to use wide characters to compile correctly. This code compiles successfully. This is pretty much all you need to get started with the system module. This was the smallest module among SFML modules. Thus, it makes sense this video is the shortest one. In the next video, we will experiment the creation of windows and process events coming from the system to understand what the window module is all about. After the system module, we will continue our investigation with the window module. The word window lets us think it's about creating windows, and your intuition is good. In this video, we'll cover how to create windows and handle its events that come along. The window module contains all the necessary stuff to bring Windows alive. That's why we'll be talking about creating windows mainly. But windows are also tightly linked to handling events. That's why processing system events is the other big part of this video. Creating a window is essential to all games because we need an area where to draw the graphics of the game. Windows can have various configurations, such as the video mode or the style. The video mode tells how big, and the style could say the window has to run in full screen mode. But we'll mainly be talking about the execution flow, which is a bit particular when it comes to Windows. To interact with the game, the player has various input devices available, such as the mouse, the keyboard, and sometimes a gamepad. The input devices deliver the information to the window, self-contained in what we call events in SFML. On the SFML website, you'll find all the documentation you need to program your games. Click on Learn, then on API Documentation. This page contains the API reference you'll be using later, and it should accompany you all along your progression in this tutorial. This page also contains a short example, often used to advertise the most prominent functionalities of SFML. The code will be our start point. Let us copy and paste it into the editor. We'll clean a little of the code because with all the comments, we cannot focus on what is important in this video. We're also refactoring a bit of the code to take out all the bits we won't need. Perhaps we should start with noticing that instead of including the system header, this time the window header is included. Since the window module depends on the system module, including the window header also results in the system header included. So we can safely move on and still use the system module. Here we are. If we compile and run the code, we should get an empty window going. Here's that window in person. When we click on the red button up here, the window closes. This example program starts with the creation of the window itself. It's parameterized with the video mode, which tells the size of the window and the title of the window. If we tweak these values a little to make the window 800 pixels long in both width and height, and change the title to Building Games with SFML, the change would appear straight after recompiling the program. The title could also have been changed with setTitle method. There isn't much to say about the title. However, the video mode requires more explanation. The SF Video Mode class is a three-component structure. The first information it holds is the width of the window. The second is the height, and the third is the number of bits per pixel, which is set at 32 by default. The bits per pixel is self-explanatory. It defines the number of bits allocated per pixel. So, if our window is 800 pixels long in both width and height, then the window contains 640,000 pixels. And each pixel will be given 32 bits or 4 bytes, which is enough to handle around 16 million colors with an amount of transparency. In practice, we shouldn't change this value unless we have a very special use case like interpolating SFML with other framework. That's why this third component doesn't show up there at the construction of the window. Generally, the video mode never changes during the game execution, but if ever you need to change it at runtime, you need to recreate the window using the create method. It takes the same parameter as the constructor. By the way, we can query the desktop video mode using the static getDesktopMode function. The result is indeed a video mode, which holds the size of the desktop. This can be useful to change the size of the window at runtime according to the size of the player's screen. For instance, I'm running Ubuntu on a very small screen, and I wouldn't like someone who creates a window bigger than my screen. Actually, I'm curious. So I will print this information out. According to the console, my resolution is 1280 by 720 with 24 bits per pixel. If you are a player yourself, you know that a game running in a small window isn't really pleasant or convenient, and that's why most of the games run in full screen mode. Well, with SFML, we can also get a window running in full screen mode, but we would have to introduce style flags first. The window behavior is customized with a set of flags to pass to the third and optional parameter in the window constructor. By default, the window is created using these three flags. The close flag means the window is closable. The window will appear with a red button to close it. The title bar flag corresponds to the frame around the window area. By setting it, you decorate the window with a frame. And the last flag is to allow windows to be resized. Let's experiment a little. For instance, if we remove the close flag, we won't get any button to close the window. See, the red button has disappeared. If we remove the resize flag, we won't be able to resize the window. The handles on each border don't show up anymore, and the button to maximize the window also disappeared. If we replace the last flag with SF Style None, we won't be getting the frame around the window. The window now appears without any title bar or frame around it. And finally, among these flags, there's the SF Style Full Screen flag, which we'll demonstrate right now. But before that, we'll quickly set up a key to quit the application, because otherwise we won't have any way to close the application afterwards. If you run the application now, you'll be getting a full screen application. You may wonder why you're getting some weird visual. You can see a portion of our desktop stretch in all directions. There are two answers to that question. First, because this will be the job of the graphics module to actually paint on this window, and secondly, because we need to select a valid video mode. When a window is meant to run full screen, the video mode no longer defines the size of a window, and instead must be carefully chosen among a list of said available full screen video modes. To get that list, we should use the static method getFullScreenModes. This function returns an array of video mode from the best ones to the worst ones. As we are curious, we'll dump the list to the console output. Notice how the list is sorted and how better resolution are printed before lower resolution. If the size of the video mode is smaller than the desktop resolution, then the image of your game is going to be stretched to fill all your screen area. That's why it's always best to create it with the best video mode. For example, we can create a full screen window by using the method front. Now that we have covered various aspects of the creation of the window, let's analyze the rest of the code. We will just revert the recent changes to get a regular window. So below we will find a while loop, which iterates as long as the window is open. Let's focus on that loop because this is a fundamental part to all games. This loop has a name. It is called the main loop, or one can say game loop too. And one iteration of this loop is called tick or frame. Think about the execution of the program. The operating system executes each line of code sequentially. That means each line is executed one by one. The very start is the entry of the main function, and then the window is created. And then what's next? If there's no loop to prevent the application from jumping to the next line, return exit _ successfully, the application would close and the window would disappear. The main loop is fundamental, and you can be sure that every game that ever existed has one. If we look inside the main loop, we will distinguish two parts: handling events and drawing into the window. The first part is handling events, and there's a lot to say about it. First off, an event variable is created with this first line of code. This event, once fed, contains all the information about an event that has just occurred. For instance, if the player clicked on the left area of the screen, this event variable will contain information like the position of the click or which button of the mouse was used. Just below, surprisingly, we find another loop. This loop iterates over all pending events that have occurred since the last tick. The function that rules this loop is pollEvent and is a method of the window, because all events are related to the window. This method takes the event structure and parameter to feed it with the actual event information. If there wasn't any pending event, this function returns false and the body of the loop is not executed. However, when any event occurs, the pollEvent method returns true and fill the event structure with the actual event data. We can experiment a bit with the handling event part to understand it better. Let's assume the user just clicked with the left button of his mouse. I would intercept in this block of code, and the first thing I would do is check the event type. The member type must be checked every time you handle an event. This is because the event itself is a union filled up with information according to the type. If you don't check the type, you cannot read the event correctly. You should know that this is a common source of error when developers get unexpected event results. In our case, to detect a mouse click event, we have to check the type against SFEvent mouse button pressed. Now we are sure this event contains a mouse button pressed information. We can write, if the mouse button was the left button, print out left button. We can also write, if the mouse button was the right button, print out right button. We might also be interested in the cursor position when the click occurred. We can find this information in the event structure by typing event.mousebutton.x and event.mousebutton.y. Let's compile and run to see what we get. This time we are running a full-screen window using the best video mode. Now I can left-click and right-click on various areas, and the information gets printed out down there in the console. That was one example to catch and handle events, but there are many more, of course. To know how to use them, I sent you to the SFML documentation, where you'll find an exhaustive list of events and the data that comes along with them. Remember that handling events is mandatory. You'll always find this piece of code which intercepts the close event and close the window when sent. This corresponds to when you click on the Close button on the top left corner of the window. After handling events, the second part of the main loop is the drawing part. Below, we can see a call to the display method of window, and this line is going to make much more sense in the next video. In the next video, we will investigate the graphics module that contains all the tools to draw on the window we just created. As we are not there yet, I will simply add a comment, "Draw here," so you can understand the window workflow. So just after handling events, the entire window is redrawn pixel after pixel to result in the next image. It's a bit like a movie at the cinema. To see motion on the screen, many images are drawn successively at very high speeds, and our eyes cannot detect the transition. Games work exactly the same way, but instead of having a set of predetermined images, these images are built up on the fly according to the player control. The display method says OK. You can finalize the drawing and update the window visual with it. But all of this might not sound clear, so let's review the execution flow of our application one more time. The window is created. Then we are entering the main loop that says, as long as the window is open, keep the game going. Right now, until the end of the application, the body of this loop will be repeated hundreds of millions of times. This happens really fast, and to give you an average idea, it should run about 60 times per second. This is where the FPS comes from actually. Then, for each frame, there might be more than one that has occurred. We process them with this embedded loop. And then we get where we were. At each frame, the entire area of the window is cleared out, and the new image is painted on it. The display method is there to validate the drawing. Redrawing the whole window might look slow, but with the newest processor and graphics card we have available, These actions are performed in no time. This is called real-time rendering. Voila! We just learned how to create a window and how to process events. This is how games work. That's it for the window module. If this is your very first time you've dealt with the main loop of a game, it will take you a little time to get familiar with it. However, do remember the main loop is the bare bones of any game. Are you wondering about the graphics result we'll get? See you in the next video to discover the graphics module of SFML. We'll see how to draw shapes, images, and text on the screen. Until now, we've covered the basics of window that included the main loop and handling events. This was to experiment the window module. This time, we're about to discover the graphics module, which has the drawing functionalities and will allow us to draw the game on our windows. This is going to be a fairly long video, since the graphics module has a large set of interesting features pretty well designed. With the graphics module, we'll be able to draw shapes, images, and texts. But we will also find out that they all inherit from common classes, allowing us to apply transformations such as rotating, moving, etc. Before we step in the content of this video, I have to bring your attention to the coordinate system orientation used in graphics computing. The orientation of the coordinate system is a potential source of confusion because at school we were taught geometry using the y-axis pointing upward, while in programming it points downwards. Therefore, if the window is 640 per 480 pixels big, the top left corner of the window is coordinate 0, 0, and the bottom right corner is 640, 480. Be careful with that. In the previous video, we ended up with this empty window. We will continue to work with it and draw some graphics on it. First thing we have to do is include the graphics module header. We have replaced the window header with graphics header because the graphics module includes the window module. Next, we must transform our window into a render window. A render window is a window, but with a rendering area that works with SFML. You would use a window when you want to use SFML with other drawing toolkits, such as Qt, OpenGL, or even a 3D engine like Ogre or Earlicht. But we want to use SFML, so we need a render window. For every frame, we will redraw the entire scene of our game, and this starts with clearing out the previous content. We do that by calling the clear method. Between clearing the window and displaying the new content, we will have the code that draws. Now if we recompile and rerun the program, the window appears in black. This is because it cleared it. I'll be starting with how to draw simple shapes. Besides having the ability to create custom shapes, SFML provides 3 predefined shapes: the rectangle shape, the circle shape, and the convex polygon. I guess their names are self-explanatory enough. When using the rectangle, we must set its size in pixel using the set size method. When using the circle, we must provide how big in pixel the circle is using the set radius method. And when working with a polygon, we must explicitly tell how many vertices the polygon has using set point count, but also where these vertices are. For this little demo, we will draw a triangle by setting up 3 vertices. Then, position the points with the set point method. It takes 2 arguments. The first is the vertex index, and the second one is the vertex position. Beware, because the order counts indeed. These 3 shapes inherit from the shape-base class, and therefore they have a common set of properties, which are the fill color, the outline thickness, and the outline color. The fill color is controlled by the set fill color method and takes a color, let's say green. Oh, by the way, let me introduce the color class of SFML, which allows to manipulate RGBA color. It can be constructed from the 4 color components, the quality of red, green, blue, and the alpha value. If I give the same amount of red, green, and blue, I'll get a gray color. The alpha value tells how opaque the color is. Thus, setting value 0 means transparent, and 255 means fully opaque. This class also comes with a set of predefined colors we can access by using two similicons, like I did here to set the color of the rectangle shape. Let's come back to the shape properties. The fill color is set at green. Now I will tell how thick the rectangle border is and the border color. This is done with the Set Outline Thickness method. And then we can set the outline color with Set Outline Color method, taking a color as parameter. For this demo, we will quickly repeat the process and add a fill color and border properties to two other shapes. I will also change the color values so we can get a more interesting result. Before running the demo, I will also change the position of the three shapes, which are done with the Set Position method. I'm doing this, otherwise they will overlap and we won't get a nice result. And finally, I will also add these shapes to the drawing pipeline with the Draw method. Remember, window.display is essential, otherwise we won't be getting the window with the new graphics content. Voila! Let's compile and run to see how it looks. As expected, we can see a green rectangle with red outline, a blue circle with a yellow outline, and a convex shape, here shaped as an arrow, filled with the magenta color and without any outline at all. This was how to draw basic shapes, but drawing images isn't any harder. To draw images, we must understand three classes which tightly work together. These three classes are SF::image, SF::texture, and SF::sprite. The first is the image class, which holds an image in memory. We can use one using its load from file method. Let's find one on the internet. SFML supports various image formats, so our choice will be quickly made. Let's pick up this one for instance. Right-click, Saving Image As. Head to the Workspace directory. I will rename it to image.png. Then create an Assets directory and put it in that directory. We can now complete the call to load from file with the relative path of the image, which in this case, assets/image.png. The image class is just a container containing the data of one image. You could query the color of each pixel, flip the image vertically or horizontally, do many things, and after modification, you can even save it back to your computer using the Save to File method. In fact, there's tons of features in the graphics module, and I cannot cover everything because this section is about discovering, not giving you an exhaustive explanation of each component of each module. That's why I'm sending you to the API documentation you can find on the SFML website to see for yourself what you can do and what you cannot do with the image class. However, something you cannot do with SF::image is drawing it on the screen. To do that, we must load the image in the graphics card, and this is the next class's job, SF::texture. To load the image in the graphics card, we must use the Load from Image method. This texture instance also holds an image, but this time in the graphics memory, not in the system memory. Although representing an image, we cannot easily modify it as we could have done with the previous class, SFImage. This time, it's a sort of read-only image. If we need this class, that's because it's much faster to draw an image when the image data is near the graphics processor. This is graphics card stuff, and we're happy not to deal with it. So just remember why we're using the texture class. But yet, this class alone is not enough to draw the image on the screen. We must use the intermediary sprite class, which is constructed from the texture. We can now draw the image by writing window.drawSprite. Let's compile and run to see what we get so far. If we still have the three shapes, this is because I left them in a drawing pipeline. So why do we need the sprite class? This is to add one level of indirection between direct rendering and image memory. Let's say we want to draw the image 2 times. With the sprite class, there's no need to load the image twice in the graphics card. I would simply create another sprite referencing the same texture image. These sprite objects are lightweight objects and can be created on the fly. Like the three shapes, sprites have properties like position, or rotation, or even a scaling factor. If I add this second sprite to the drawing, I'll be getting two images drawn. Let's see the result. This time, the second image is drawn with different geometrical properties while still using the same texture image in memory. If we look back, we must deal with three levels: SF image, SF texture, and SF sprite. That's not really convenient. In fact, for most usage, we'll only be using the texture and sprite class. We can shortcut the code by suppressing the image object and load the texture directly from the file on the disk using the load from file method. The third drawing entity, SFML, provides its texts. It's frequent in games to have the need to display text on the screen. Of course, we could still display an image containing the text pre-rendered, but that'd be a foolish solution for changing a text. Instead, we use the SF font and the SF text class. First, we need a font to work with, so I'm going to browse a well-known website to get fonts, dafont.com. Any font is fine since it's just a demo. Let's choose this one. Once downloaded, we need to extract the font to the assets directory of our game. I'm also renaming the font to font.ttf. The font class that holds each character image. We load the font with the load from file method. Then, with the font object, I can create as many text as I want using the font. In fact, the idea is somewhat similar to SF::texture and SF::sprite. Instead of having SF::texture to hold the image, we have here the SF::font. And instead of SF::sprite, we have text. We can create as many text as we want. It will use the same font, and the memory consumption is kept low. To use text, you first need to associate the font with the setFont method. Then you define the text with setString. You can customize text with the color, the character size. Check the API documentation to have an exhaustive list of what you can do. For instance, I will change the color with setColor and change its position to get it centered. Let's also increase the character size with the setCharacterSize method. And finally, I will add it to the drawing pipeline to get it drawn. Compile with Make and run. The text OLA SFML appears at the center of the screen and is colored in red as expected. This was the first part of the graphics module video where we've just seen how to draw shapes, images, and texts on the screen. Like you could see, we ended up with quite a large amount of code. Thus, I would advise you to digest the content before starting the second part. The second part is about deepening the graphics module. We'll see how to create our own drawing entities and render on something else than a window in the next section. Take a break, and we'll continue when you're back. Welcome back. In the previous section, we have taken a look at all the various modules we have and have taken our time investigating SFML through and through. This is Section 3, and from now on, the real business begins. In this section, we'll write the first pieces of our game to give it a first shape, hence the title of this section, Shaping the Game. In the next videos, we'll be implementing the foundation of the game. It will all start with writing the game loop. Then, we'll have to divert the game with game states. And finally, we'll model the entities of the game and animate characters. Let's get down to business. In this video, we'll start the implementation of our video game with the game loop. If you recall the video 2.2, Discovering the Window module, you already know the game loop, or sometimes called main loop, which is always the start point when building video games. Therefore, we are going to take a closer look at the game loop, but also the handling events, such as when the player moves the joystick, for instance. If you followed all the videos until here, you already know we'll be building a clone of Pac-Man. Let's analyze the original game to better clone it step by step. Pac-Man is an arcade game developed by a Japanese company, Namco. This game was first released in the 1980s and was very popular in game centers which had the Pac-Man machines. This is because at the time, few people had personal computers at their place. That's why the first people who had the chance to play this game played it on these arcade machines. In fact, to spice things up, we will pretend we are hired as a SFML programmer by Namco to write their next commercial success game, Pac-Woman. Pac-Woman is going to be their next title. Instead of controlling Pac-Man, we'll be controlling a female version of him, Pac-Woman. It will be about controlling this tiny creature in a two-dimensional maze with ghosts to dodge and fruit to collect. When Pac-Woman eats a super dot, ghosts become vulnerable and she can eat them back. However, after conducting a brief survey among Pac-Man players, Namco realized that the main complaints were about the maze being the same and too small. That's why they asked us to implement gigantic mazes with a camera tracking Pac-Woman. We'll see this aspect in later videos. As a good game programmer, we will start with grabbing a sheet of paper and start an analysis of the game we are asked to develop. The first thing that will bring our attention is the interaction the player has with this machine. Basically, the player will come over on one of these exact same machines, insert a coin, and play the game until you lose. During the game, the player controls Pac-Woman with an analog stick moving along two axes to move her in 4 directions. There's also a start button allowing the player to start the game after he has inserted a coin. And lastly, there's a coin receptor for the player to insert coins. Inside our game, we will emulate these 3 forms of input. Back to Genie. This time, I have erased all the previous code which were meant to demonstrate SFML functionalities. I reverted all the changes and it's now a clean state. I just kept the main function and the inclusion of the graphics module header because it's needed to implement the game loop. As seen during our investigation of the window module, the game loop is mandatory and controls the lifetime of any game. Therefore, we are going to start by writing it. Quickly, it consisted of opening a window. I'll give it a standard size for now, 640 over 480 pixels is fine, and a title, Pac-Woman. Just after comes the game loop itself, which terminates when the window closes. This is the action performed when the user clicks on the red cross button. Inside, we need to read the events delivered to the application. It consists of creating an event structure and use the poll event method. While this poll event returns true, it fills the event structure with the actual data and we have to read it. Right now, the only mandatory event to handle is the close event, which is sent when the user clicks on the red cross button. And the last bit is refreshing the content of the window. This is done in 3 steps: erasing the previous content with clear, drawing the new content. There's nothing to draw, so I will add a comment, draw here. And the last step is forwarding the new content to the screen using the display method. I will compile and run it just to be sure I didn't miss anything. Voila! It works perfectly. But I really like oriented object programming, and I find this code is a bit too old-fashioned. That's why I like to turn the whole main loop into a C++ class named Game. Let's create 2 new files, game.hpp and game.cpp. To create new files in command line, we write touch followed by the file name. This is an important standard command. After creating the 2 C++ files, we have to list them in the CMake script as well, so they get added to build the system. Now we have to rerun CMake to update the makefile script. And finally, let's open the 2 new files. Once again, I will spare time and use the console. Just type Genie, followed by the file name, and they appear in front of you. Magical and handy, isn't it? The game class. Since this is a header, we better protect it from multiple inclusions. Usually, I name these macros after the project name, followed by an underscore, then the file name, followed by HPP. The game class has a default constructor. The whole main loop logic is self-contained in the run method. And finally, it has a SFRender window attribute. Now I will quickly split the previous game loop I wrote in main.cpp and put each of the pieces to their relevant place. The window construction has to be moved to the constructor, and the game loop itself has to be moved to the run method. We have to adapt a little to the code, such as to add the m_ prefix to the window. Now there's nothing left in the main function. We just have to create the game instance. I will name it PackWoman and call its run method, which will return as soon as the window is closed. Let's not forget to include headers correctly. If I compile and run this code, it should give me the exact same result. Now let's have a look at the input. We saw that there are 3 possible interactions with the arcade machine. Inserting a coin, I stimulate it with the insert coin method. The press button method will obviously correspond to pressing the start button. And the third interaction is moving the joystick, which I will stimulate with the move stick method. I've added here a 2-dimensional vector in the parameter. This is so that the stick can move in 4 directions. Anytime there's a change in the stick direction, this method has to be called with either -1, 0, or 1. For example, if the stick is moved on the left, then this method is called with a vector whose x value is -1. We'll leave the implementation of these 3 methods empty for now, because we first have to detect these interactions. Detecting the interaction with the machine is done in the event loop. Since we're running the game on a PC and not on an actual arcade machine, we will use the keyboard and map each input to it. As such, we could press the I key to stimulate inserting a coin and the S key to press the start button. As for the joystick, we'll use the 4 arrow keys. Be careful with the inverted coordinate system. When I press the down key, PackWoman should move downward and thus positive in the y-axis. To test this code, I will output some text when these 3 methods are called. Let's compile and run it. Now if I press key I should get insert coin, S for press button. And when I press any directional keys, I get move stick. Perfect! The job of this video is done. We've successfully implemented the game loop. The next video will be about game states, which will allow us to divert the game flow. Join me there. In the previous video, we understood the importance of a game loop and implemented it for our PackWoman game. In this second video, we'll be talking about the game states, which is the second step in implementing the foundation of a game. Implementing game states will allow us to divert the game flow. This is the first point we're going to take a look at. Then we'll see the FSM pattern, which is used to implement these game states. Let's start this video with a bit of theory. No game on Earth comes without a couple of buttons or some sort of a menu for us to get ready before playing the game. Games aren't plug and play, and instead, once launched, we usually go through a loading screen, a menu, and so on. Each of these steps, the loading screen, the menu, and the game itself, has its own input logic, drawing logic, and we'll see how to scatter these logics in their respective game states. All games have this notion of game states in some way. Once again, let's start with analyzing the original Pac-Man game and try to find back its game states. That's why I've prepared a couple of screenshots showing me playing Pac-Man. At the very beginning, the menu shows up displaying a button, Play Game, for the player to start the game. As long as we don't do anything, the menu stands there idling until the player clicks on the Start button. This is the very first game state. After we hit the gameplay button, the maze shows up with its entities, Pac-Man, the 4 ghosts and dots, but we aren't allowed to play the game yet. Actually, we're in a get ready state that blocks any input, giving the player a few seconds to get ready. This is another game state. A little later, the game starts and we're allowed to control Pac-Man with the stick. This is the third game state, and we'll call it the playing state. Later, the player will either lose or win, and yet the game will go through other game states again and again. We could go on and spot other game states, but we'll stop here. What is important to understand is that game states models the execution flow of the game, and they allow and restrict the access to other game states at the same time. We won't implement game states exactly the same way as in the original game, so let's take a look at how we are going to handle game states in Pac-Woman. I will use a state diagram to model the execution of our game. The first state is no coin. Remember, our game is running on an arcade machine, and it makes sense that players pay to play. Thus, before a player comes in and inserts a coin, the game state is no coin and a menu is displayed. When a coin is inserted, the player is allowed to play and the game goes into the Get Ready state. In this Get Ready state, the maze is shown, a message, Press Start, is displayed, and the game is waiting for the player to hit the Start button. Once the Start button is clicked on, the game starts and the player can show off their amazing Pac-Man skills. It doesn't matter if they are a hardcore gamer or a real noob. Sooner or later, they will either lose or win the game. From now on, 2 routes are possible. Let's investigate the lost route. The player loses when they have consumed all their 3 lives because they are only allowed to get caught by the ghosts 3 times. When the game reaches the lost state, instead of simply going back on the no coin state, we will allow the player to continue by inserting another coin within the next 10 seconds. If a coin is inserted, 3 more lives are given to the player and the game jumps to the Get Ready state. However, if no coin was inserted by the end of these 10 seconds, the game is definitely lost and is back to the no coin state. That was for the lost route. Now, what if the player actually eats all the dots and wins? In this case, the game goes into the won state where a message, "You win," is displayed. A few seconds later, when the user has had enough time to read the message, the game goes back to the Get Ready state to let the player start the next level, with probably another maze layout and with a higher speed to make the game harder every time the player wins. Back to the Ready state, he will have to hit the Start button again to start, and the loop is looped. Before we start with the implementation, the last piece of theory to cover is how we are going to implement these game states. And the answer is by using the finite state machine pattern. The idea behind this pattern is simple. One machine can be in a defined state of states, but this machine is only in one state at a time. The previous slide contained a state diagram where only one game state is active at a time. This is exactly the same idea. In our case, the game class is the machine, and the game states are the machine states. At the beginning, the current state is no coin state, and as soon as the player inserts a coin, it jumps to the Get Ready state, and so on. The machine will never be in 2 states at a time. To implement this pattern, we're going to use a pointer to the current state. By using this pointer, which can only point one game at a time, we will ensure only one game state is active at a time. Let's get down to the implementation. To implement game states in a game, I generally start with a new class, GameState, which is the base class of each game states. Inside, I use an enumeration listing the game states. By using an enumeration, I make the code more readable. In our game, we have 5 game states: no coin, get ready, playing, won, and lost. Each game state needs to fulfill the 3 fundamental steps of a game tick, which are handling input, updating the game states, and drawing the new content. But in our particular case, the input is limited to inserting a coin, clicking on the Start button, and moving the stick. And we already wrote them above, so let's copy them and replace the handle input method. It results in 5 methods. Since this class is meant to be subclassed in order to provide different behavior, we have to make them pure virtual because they really are meaningful for each possible game state. The GameState class deserves its own C++ file. That's why I'm going to create GameState.hpp and GameState.cpp. Then I will move this GameState class to GameState.hpp file. I won't forget to protect the header. And the last touch is adding them to the CMake build script. We won't forget to regenerate the build script either by running CMake. Now we have to update the game class to only run one game state at a time. To do that, I will include the game state header first, then I'm going to add the game state pointer m_current state. When a game state is current, it has total control over the execution of the game. That's why in the run method, we need to make forward calls to the current state at every tick. Let's start with the input methods. Instead of calling local input methods such as insert coin, press button, and move stick, we call the current state ones. By the way, we can remove the local implementation of these methods. And finally, let's forward the call to the update method with the elapsed time of the course. And the same for the draw method. By forwarding the main calls this way, the current game state sort of becomes master of the game execution. But since the current game state has absolute control, it's also responsible for deciding and jumping to another game state. Therefore, we have to implement the way to change the current game state from within the game state. A simple change game state method will do the trick. It takes in a parameter as the game state ID. We'll leave the implementation for later because we first have to implement each concrete game states one by one. I'm going to start with creating a concrete game state acting as a template. Every game state inherits from the GameState class. It must implement its 5 pure virtual methods. I will give them an empty implementation for now. Let's not forget to include the game state header. Each game state should have a local pointer on the game instance because they're responsible for changing the current game state. That's why all game states have to take a pointer on the game instance when constructed. For each concrete game states to get an access to the game instance, I'm going to implement getGame method in GameState. If I didn't miss anything, I should get a compile-able code. I forgot to include the graphics module in GameState. I will now duplicate the concrete game state, no coin state 4 times since our 5 game states will have the same code. It's a bit laborious, so give me time to update each occurrence. Hopefully, with the Find and Replace feature of Genie, I can speed up the process. This is also the foundation of the game. That's why it generates quite a large amount of code. In later videos, we're going to fill all these methods one by one. I'm done with implementing the 5 game states. Let's compile to check if I haven't made a mistake. Great, it compiles just fine. Let's go back to the game class because we have to update it to instantiate these 5 new game states. And we'll be doing that using an array. In modern C++, this is done by using the standard array structure. It's an alternative to native C array, which provides support for the iterators and all the algorithms we can find in the standard library. It needs to be parameterized with the type and then the size of the array. For the number of game states, I could simply count them 1, 2, 3, 4, 5, and write 5 here. But what if later we add one more game state? There would be 6 in total, and if I forget to update this number, I would just introduce a bug. Instead, I will write game state count and terminate the enumeration list with a new entry count, which given the C++ specification, we should get the value 5 because each of the items are given values incremented by 1. We will initialize this array in the game constructor. For each entry, the corresponding game state is created. Each game state takes the game instance in parameter. And finally, we have to deallocate each game state when the deconstructor is called. This is where using modern array comes in handy, because we can easily loop it and use the delete operator. Now we can finalize the implementation of the change game state method. It's just looking up in the game states array with the game state ID and updating the current game state pointer. When the game is launched, the initial game state is no coin, so let's change that in the constructor. Let's check if the code compiles or not. Hi, it does. In this video, we saw how to implement the foundation of our game. The code grew up quickly, but it was necessary. Hopefully, the next piece of code will naturally fit in each of these game states. The next video will be about implementing the navigation. We'll understand how flexible our code has become after implementing game states. Hi there and welcome back. In the previous video, we implemented the 5 game states. Now we're going to use them to implement the navigation of the game. We'll be dealing with resources for the first time. That's why we're going to start by taking a look at handling resources. And since the implementation of the game states was all about diverting the game flow, we're going to see how this can be done. Before we step in, I'd like to remind you of the state diagram of the previous videos. The 5 blue ellipses represent the 5 game states we implemented. The arrow represents the logic to go from one state to another. This is what we are going to do, writing the logic for our game to go from game states to game states. To fill each of the game states with their respective logics, we'll be needing resources. So, what are resources? Resources, which can also be assets, can be images, fonts, sounds, and actually all the external files one application needs to function. Let's take a look at our assets directory. Like you can see, our game is made of 1 font file and 2 images. There aren't many, but still, we have to ensure they are loaded only once in memory and that we can access them from anywhere in the code. The game instance seems to be the most appropriate place to hold our resources. I'm going to add 3 attributes. SF font for the single font file, SF texture logo for the logo image, and SF texture for the other images, which are all packed in one image or one texture. In the constructor, we will initialize these 3 attributes by using their load from file methods. When the font file fails to load, this method returns false. The question is, in the case of failure, what are we going to do? Well, we cannot really recover from these errors, and the only action we can take is terminating the application. The proper way to achieve this is by throwing an exception. First, let's enable these exceptions by including the exception header. Then, when load from file returns false, we throw a runtime error exception saying unable to load asset texture. Why do we use runtime error exception? If ever SFML fails to load the texture, it is most likely because it cannot find the file. Therefore, this is an environment error and not a logical error. We use standard runtime_error for non-logical errors. Later, when shipping the game, we will have to pay attention to shipping our assets along with the executable. If we look at the game state, we will notice that the game instance is shared across all game states with the getGame method. Therefore, providing accessors for these resources is a good option, as we'll get access to each resource from each game state. Accessors are nothing more than get methods. Let's implement one for each. We are done with handling resources now. Let's start with the very first game state, no coin state. When our game is in no coin state, a black screen is displayed with the logo, and also a text insert coin is displayed. We need a sprite attribute to display the logo and a text. Inside the constructor, we can start with initializing the logo. It consists of setting the texture, which we can retrieve from the game instance. The position is 20, 50. Then the text instance is initialized with the font. And the text is insert coin. And finally, in the draw method, the text and the logo have to be drawn. After this, we'll include game.hpp header as well. Now let's check the result. When the game starts, the game runs the no coin state, which displays both the logo and the text. Obviously, the text is misplaced and should appear centered. The problem with text is that they can grow or shrink as the text itself is modified, and positioning them can be tedious. To ensure we position the text where we want, we can modify its origin and place it at its center. So when we write text.setPosition 240, 150, the text appears centered at this position. I'm going to write a small utility function to automate this task. The function is called centerOrigin and takes a SF text in the parameter. First, we need to know how big the text is by calling getLocalBounds. The origin is then modified to be at half the size of the text. Now, just before positioning the text, I can write centerOrigin with the textIn parameter. Let's check if the result is any better. The result is much better. Later, we can change the content of the text, and it will still remain centered. It looks nice, but it would look nicer if the text, insert coin, was blinking after every few seconds. This behavior is easy to implement. I'm going to add a Boolean display text as attribute. Then initialize it with the value true. Then I will change the draw method to display the text only if the display text value is true. The only last task left is reversing the Boolean value every half second, and this is done in the update method, which provides us the elapsed time. A static time buffer initialized with time 0 will retain the accumulated time. When this time buffer exceeds half a second, the display text value is inverted and we subtract 1 second from the time buffer. If I run this code again, it should blink now. Wonderful! Now what? We have a beautiful logo displayed with a text asking the player to insert a coin. So when the player actually inserts a coin, the current game state needs to be switched to the Get Ready state. Implementing this behavior is really easy. When the Insert Coin method is called, I get the game instance, then call Change Game States with Game State Get Ready. If we run the code again, and if I press the I key, I should be getting a black screen. This is because the Get Ready state takes over, and it draws nothing onto the screen just yet. Let's continue with the implementation of the Get Ready game state. Once the player inserts a coin, a message Get Ready should be displayed until the player hits the Start button. So I'm going to add a text attribute again. In the constructor, it has to be initialized with the font. The text is, "Press Start when you're ready." I will also change the character size to 14. Then I will center the text by using the utility we wrote earlier. And finally, add the text to the drawing pipeline. The only task left is changing the state when the player presses the Start button. In the Press Button method, we have to call Change Game State with Playing. Let's check if it works. Great! When I press the S key, I get to the playing state. Again, the playing state results in a black screen because we haven't implemented it yet. However, this time we can't do much since we haven't created the maze yet, or modeled the entities of the game such as the Pac Woman, the ghosts, and so on. Instead, to continue with implementing the navigation, I will simulate a jump to either the lost state or the won state. In the Move Stick method, if the player moves the stick to the left, he loses the game. And if he moves it to the right, he wins. Let's continue with implementing the lost state. When the player loses the game, he gets 10 seconds to insert another coin. If he inserts one, he gets 3 more lives and can continue to play. However, if he doesn't, the game goes back to the no coin state. We need one text attribute to display the message, "You lost," then a time buffer, which I will call Countdown, and also another text to display, the countdown. In the constructor, I have to initialize the text with the font. The text is "You lost," and I will also change the character size to 42. Then I will position the text using Center Origin, and then the position 240, 120. The countdown buffer can be initialized with time 0, and the countdown text with the font file. I will also change the character size to 12. And finally, position the text. Below in the Update method, I will increment the time buffer with the elapsed time. Then, if the time exceeds 10 seconds, the game state is changed to no coin state. And finally, let's update the countdown text. Let's check if it works. When I press the left arrow key, the lost game state is active. After this, in the game.cpp file, in the run method, define a clock attribute. I will name it as frameClock and change the current state update method to frameClock.restart. The last game state to implement is the won state. There's nothing much to do here but to display a text, "You won." Let's add a text instance. Then I will initialize it exactly like the previous one. The text is "You won." And finally draw the text. In the update method, I will declare a static time buffer. Increment it with the elapsed time, and when it exceeds 5 seconds, change the game state to "Get Ready." Of course, later, we'll add the logic to increase the difficulty of the level. Let's check if it works. Perfect. In this video, we have successfully enabled our characters a sense of direction and given them the ability to move around, or enabled us to control them through the maze. The next video will be about modeling the entities of the game. Remember, in Pac-Man, there are ghosts, a bonus, dots to eat, and let's not forget the main character, Pac-Man. All these entities need to be drawn on the screen, and some of them have common properties. We will use inheritance and implement all of this properly. See you in the next video. Hi everyone. In the previous video, we looked at controlling the characters with controllers for our player to be able to move. In this video, we're going to model the main entities of our game. When the game reaches the playing game state, the maze is displayed and various entities appear on top of it, such as Pac-Woman, ghosts, the dots, and eventually bonuses. All these things are called entity, and they deserve their own class, encapsulating their own logic. Along with modeling entities, we're going to take a look at using SF drawable and SF transformable like we did in Section 2, but this time in a real-life example. We will also see how to display a subrectangle of an image, since we'll be dealing with sprite sheets. Let's get down to the business. To start, let's have a look at the original Pac-Man game. On the maze, which is static and won't change, we recognize various objects on it with which Pac-Man interacts. Firstly, we have the dots. The purpose of the game is to collect them. I guess it's unnecessary to explain what super dots are for. Then, from time to time, a few bonus objects appear, which increases the score when we collect them. In this screenshot, there aren't any, but they are usually shaped as fruits. We also have ghosts, which Pac-Man doesn't want to run across. And finally, we have Pac-Man itself. These 4 kinds of objects are called entities, and they have their own logic, and we're going to model them one by one. Among these entities, we can recognize common behavior among them. That's the case for Pac-Man and ghosts. Both are animated and run through the maze by following the same collision logic. They collide with the walls of the maze, preventing them from passing through them. And they can also move in 4 directions. We're going to use inheritance in order to avoid logic duplication and create a common base class named character. One last thing before we start modeling entities: sprite sheets. The image in front of you is called a sprite sheet because it groups every single image of the Pac-Man game into one big image. Games do that because rendering is made much more efficient when the GPU works with a single texture. If you've already heard of reducing texture bind to increase performance, that's exactly all about that. Of course, for the tiny game we're developing, it's not a big deal. SFML can display thousands of images without any performance issues. However, when the scene becomes bigger and has much more content, packing your images into sprite sheets is what you want to do. As for our game, we'll also be using this technique. Let's implement the 4 entities now. I went ahead and already created the 5 pair of C++ files we'll be needing. Each header is properly protected from multiple inclusions. I also updated the CMake script accordingly and reran the CMake command. Let's get started with the most simple entity, the dot. It would probably be an overkill to create a whole class for the dot and superdot entities, since they are merely just a circle shape. And SFML already has such a class. Instead, we'll create the getDot and getSuperdot functions both returning a circle shape. Let's not forget to include the graphics header because we're using SF circle shape. Their implementation is straightforward. This is just returning a circle shape properly set up. Dots are going to fit in 32 pixels large cells. So let's make them 8 pixels large. The color of a dot is white. And I will also change its origin so they appear centered. The implementation of getSuperdot is exactly the same. Instead of 4 pixels for the radius, we are going to set it at 8 pixels and change the origin accordingly. I will also include dot.hpp header. Let's continue with the bonus class. This time we are going to create a class, and this class inherits from SF Drawable and SF Transformable. Therefore, we need to include the graphics header as well. And any drawable must override the draw private method. In our game, bonuses are also shaped like fruits. Let's have a look at our sprite sheet. We can see a banana, an apple, and a cherry. Our bonus class has to reflect that, so let's define a public enumerator named fruit. We have banana, apple, and cherry. To display the corresponding fruit, our class needs to access the sprite sheet. Let's add a constructor taking a reference on the sprite sheet texture. And also an attribute of SF Sprite. Along, let's also add a setFruit method so we can customize the bonus appearance with one of the 3 fruits. In the constructor, we have to set up the sprite to point on the sprite sheet texture. By default, the appearance is a banana. To customize the bonus, we'll have to call the setFruit method. Be careful, this is new stuff. Currently, our sprite is set up to display the whole texture image by default, but we only want to display the subimage corresponding to the fruit. We can do that by changing the region of the image to display. We have to use setTextureRect with a rectangle telling where the subimage is. The first parameters are the left top corner position of the subimage, then the two last are its size. I already inspected the image and retrieved these values, but usually just open an image editor and note the information somewhere. The implementation of the draw method is trivial. Just draw the visual and don't forget to combine graphical transformation. The last touch will be to change the sprite origin so fruits appear centered. Since each of the fruits are 30 pixels large, their center is at 15, 15. We're done with bonus. Next are the characters, Pac-Woman and Ghost. Both Pac-Woman and Ghosts are drawable and transformable. Let's add this behavior to their common base class character. Then both Pac-Woman and Ghost inherit from character. The drawing logic is different, so it makes sense the draw method is defined locally. There's going to be a whole set of common behavior to implement in the character class, such as colliding with walls, but we need to wait until we implement the maze, which will take place in the next section. In the meantime, not to leave the character class empty, let's implement the speed behavior. The speed simply is a scalar value, and we have two accessors, setSpeed and getSpeed. The speed is expressed in pixels per second, so let's set it at around 3 pixels for now. We can adjust this value later. Also, include the character.hpp header. Pac-Woman has her own set of specific logic too. The drawing logic is simple. This is just an image to be displayed. However, if you recall the original game, Pac-Man opens and closes his mouth alternatively while he runs through the maze. This is called an animation. We're going to implement a similar feature, but it will take place in the next video. There's also another behavior specific to Pac-Woman that we want to implement, the dying behavior. When Pac-Woman collides with a ghost, she dies, eventually by calling the die method. Let's also implement the isDead method and maintain a Boolean isDead. The implementation is straightforward. Include the Pac-Woman.hpp header. In the constructor, we have to set up the visual attribute. And at the beginning, Pac-Woman isn't dead. As usual, we want to work with the origin positioned at the center. Because Pac-Woman's image is 40 pixels large, the center is at 20, 20. In the die method, we set m_is_dead at true. IsDead method simply is returning the Boolean. And in the draw method, we display the visual only if Pac-Woman isn't dead. Also, don't forget to combine the transformation. We're going to leave that class for now and take care of animating Pac-Woman in the next video. The drawing logic of a ghost is as simple. This is also an image. Ghosts are also animated, but we'll take care of that later. Ghosts become vulnerable when a superdot is eaten by Pac-Woman. We're going to call that the weak state. And the opposite is the strong state. When ghosts are strong, Pac-Woman dies when they collide. However, when ghosts are weak, ghosts die. Along, there's going to be isWeak method and setWeak, taking a duration in parameter. We also need a Boolean isWeak and a time weakness duration. After this, we will also add pacwoman.hpp header and a default constructor. In the ghost constructor, we set up the visual attribute. IsWeak is set at false, and weakness duration at 0. Ghost images are also 40 pixels large, so let's set their origin at 2020. SetWeak consists of changing the Boolean value at true and initializing the duration attribute. IsWeak is trivial. And finally, the draw method. We won't forget to combine transformations. Since both Pac-Woman and Ghost classes are not functional yet, we will leave the testing to the next video. We're making a lot of progress. In this video, we covered modeling our entities so they can be easily distinguished and our viewers can relate to them. Modeling dots and bonuses was trivial, but we're missing animation for Pac-Woman and the ghosts. That's what we're going to do in the next video, animating characters. We will see how to implement an animator to display the correct frame at a given time. Welcome back. In the previous video, we started to model characters, but we quickly realized we're missing a way to animate them. In this video, we'll learn how to create an animator, then complete the implementation of both Pac-Woman and the ghosts by adding their corresponding animations. Animation is performed over time. That's why we're going to take a look at handling time. Then, once we've fully understood and mastered, we'll go ahead and see the implementation of a typical animator. Let's have a look at the animations we have to implement. As Pac-Woman and Ghosts run through the maze, they're slightly animated. Pac-Woman opens and closes her mouth alternatively, and Ghosts look like they're dancing a little. During the game, Pac-Woman can pick up super dots, which make Ghosts vulnerable for a short time. In the previous video, we called it the weak state of a ghost. When the ghost is weak, his appearance changes as well as his behavior. That's not all. When Pac-Woman is caught, she dies and plays this last animation. To implement these animations, we'll need an animator. Let's have a theoretical look at that animator. Playing an animation consists of drawing successively different images to result in a smooth and appealing object moving on the screen. Changing the image to draw is the animator job. The animator is an object which is first initialized with the animation data. Since we use sprite sheets, our data are the subrectangle information of each subimage. We'll name these rectangles frames and use the add frame method. To perform the animation, the animator needs to be time-aware and is therefore fed with the elapsed time. To perform the subrectangle change, we'll use the animate method, which takes a sprite reference. It makes sense that the animator takes care of changing the subrectangle, since it has all the information to do that. And finally, two essential methods, play and isPlaying. The first is called with the animation duration, and a Boolean telling whether or not it has to loop the animation once finished. The second method allows us to take action when the animation is over. I went ahead and created an empty animator class in their own C++ files, and we're going to fill its implementation. As you can see, the interface is already defined too, so let's go through it. The add frame method is to add subrectangle data. You can see there's a vector defined below. Next are the play and isPlaying methods. They tightly work with these three attributes. There's also the essential update and animate methods. And finally, one last attribute to save the index of the frame currently played. In the constructor, we have to initialize the attribute. The animator is not playing anything when constructed. We have also included the animator.hpp header. The first thing we have to do when using an animator is feeding it with the data. Adding a frame simply is adding to the frame vector. Then, we have to play the animation using the play method. Inside, we simply save the settings by updating the corresponding attributes. isPlaying simply is an accessor returning the isPlaying Boolean. The biggest part takes place in the update method. Its job is to compute the current frame index. But let's implement the animate method first. According to the current frame, it updates the texture rectangle of the sprite. The update method has to compute the correct frame index, so when animate is called, the sprite is updated with the correct subrectangle. First, if the animator hasn't been yet asked to play something, don't do anything. To keep track of time going by, we're going to use a local time buffer initialized at 0. This time buffer is then incremented by the elapsed time. Now we have to compute the duration of one frame. This is the result of the animation duration divided by the number of frames to play. Time division is only defined with a floating point value, so we have to cast the size into a float. Then, if the elapsed time is greater than one frame duration, the current frame index is incremented. And we decrement the time buffer by the frame duration. In between, we need to handle when the frame index is greater or equal to the number of frames. In this case, we stop playing the animation unless the loop is set to true. If the animator has to loop the animation, then the frame index is reset to 0. The last touch is to change if to while, because think about it. If the application is lagging because the CPU is busy with other applications, this update method can be called with an elapsed time really large and which would result in skipping 2 frames, perhaps more. By changing if to while, we handle these very rare cases, but this is to code the game properly. Our animator implementation is completed. Now we are ready to finish Pac-Woman and Ghost implementation. Pac-Woman has 2 animations, opening and closing her mouth and dying. Let's add 2 animators, one named Run Animator and the second Die Animator. Include animator.hpp header. Before being dead, we introduce the notion of dying by an additional Boolean isDying. Pac-Woman also gets the isDying method. Let's also add its trivial implementation. In the constructor, we add the initialization of the isDying Boolean. The first thing we have to do when using animators is setting them up with the animation data. Before starting this video, I opened the sprite sheet and took note of this information. And finally, we launched the run animation using play. 1/4 of a second should be enough to display only 2 frames, and we loop it. We have to update the die method, so when Pac-Woman dies, the dying animation starts. Unlike the run animation, we don't have to loop it. At every frame, Pac-Woman is going to be updated with the elapsed time. The code takes place in the update method. Inside, we need to update in turn the 2 animators. If Pac-Woman isn't dead nor dying, the run animator is updated. The animator computes the current frame index with update. Then we'll pass our sprite instance so it can update the subrectangle. Otherwise, this is the die animator we have to update. If the die animator has finished playing, that means Pac-Woman is definitely dead, and we can update the attributes. That's it for Pac-Woman. The Ghost also uses the animator, include animator.hpp header, and implement in the same fashion the strong and weak animator. Ghost entities are also updated. Now add Pac-Woman.hpp header also. When using animators, our first job is to initialize them with the animation data. Again, I noted this info beforehand. And at the beginning, the strong ghost animation is played. When the ghost is set weak, the weak animation is played. When the ghost is updated, we have to update the 2 animators according to whether the ghost is weak or strong. When the ghost isn't weak, the strong animator is updated. And we also update the visual. Otherwise, the weak animator is used. There's one last thing we need to handle. If we look at the setWeak method, we give a duration of the vulnerable state of a ghost. When this duration expires, the ghost goes back to the strong state. We handle this in the update method as well. If the ghost is weak, then we decrease weakness duration, which is merely a time buffer. Then, if this time buffer reaches 0, the isWeak attribute is updated, and we replay the strong animation. It's been 2 videos since we started to implement Pac-Woman and Ghost. What about some testing now? Let's open the GameState header file include their two headers, and add two attributes to playing state, pack-woman and ghost. In the constructor, we need to initialize pack-woman and ghost with the sprite sheet. We'll move these entities a little so they don't superimpose. To interact with them, we'll use Insert Coin to kill pack-woman. And press button to set the ghost vulnerable 3 seconds. We need to call their update methods as well. And finally, draw them. Let's have a look at the result. By default, pack-woman plays the run animation and so closes and opens her mouth alternatively. If I press the I key to insert a coin, pack-woman dies. If I press the S key to press the Start button, the ghost becomes vulnerable for 3 seconds. Everything appears in order. However, before we move to the next section, let's review what we covered in this section. We began our section with understanding and implementing intrinsic features, such as the game loop and game states, which form the skeleton of our game. Then we took a look at the navigation between the various states and enabled our entities with movement controls so we could move them like puppets. And finally, we modeled and animated our characters to look alive and kicking. Let's move to the next section now, creating the maze. An entire section is dedicated to the maze because we have many topics to cover. Firstly, the rendering of the maze. Then we have to implement the collision logic. And finally, we also have to add camera so we can play on gigantic mazes. See you in the next section. Hi everyone and welcome to Section 4. In the previous section, we implemented the foundation of our game. We sort of created the skeleton by paying attention to the game loop and the game states. Then we foresaw what is ahead and started to model the entities of the game. The next major step is the implementation of the scene. And since we're building a Pac-Man clone, this section is going to be about creating a maze. If you remember the earlier videos when we set the objectives, we said we would go for large mazes with a camera tracking feature. We'll get to that in a while. First, we're going to start with figuring out the best way to create and edit these gigantic mazes. Then, we'll implement the logic to efficiently render mazes. Later, we want our characters to move logically on this maze. That's why we need to implement their navigation logic. And at the end, we're going to take a look at the most advanced feature of our game, a camera that tracks pack-woman's position. Let's get started. Now we move on to the first video of this section that deals with loading levels and the rendering of the maze. In this video, our objective is to display a simple maze on the screen, which we are going to enhance in the later videos. This video is divided in two main parts. The first part of this video is going to take a look at choosing the appropriate data structure for the maze. Then, the second part will be about implementing the rendering logic. But first off, a chunk of theory before we start. There are thousands of ways to implement our maze. However, I'm going for what seems to me the most natural and easy solution to get a result similar to the original Pac-Man game. Behind this maze, there's a grid. This grid is a two-dimensional array that represents essential information like wall, dots, and empty cells, etc. We're going to do the same, but instead of having different mazes having all the same size, we're going to model a very large maze. When loading a new level, we need essential information, like how many ghosts we have on the map or where Pac-Woman starts. On top of that, we also have dots. The main goal of Pac-Man is to collect all dots without being caught by the ghosts. And among these dots, we have super dots. There is a lot of data to represent, and we need a solution. Usually, people tend to hard-code data straight in their code or in a text file, like shown on this slide. However, there's a few drawbacks to this solution. It's not easily readable and not explicit either. It's also prone to errors. But the worst of all is, we need to parse it. Parsing consists of opening this file, then handling lines after lines, characters after characters, converting into numbers, etc. What a tedious solution for such a simple game. In our Pac-Woman game, since we'll provide various maps of various sizes, we need a better solution. We're going to use regular images. You might wonder, what the heck is this? The answer is a simple image, here 15 pixels large, and which could be named level.png. You can guess from the image, the black pixels are for walls and white ones are for empty spaces. The white cells are where Pac-Woman and ghosts can move. Then, come to wonder what the other colored pixels are for? The answer is, for super dot, the Pac-Woman's initial position and the ghost's initial position. Then we have two ghosts, who start where the two red pixels are. And lastly, we have 6 green pixels representing 6 super dots. This solution is going to work because an image is just a grid of pixels, just like our maze. But using this pixel color convention, we can easily create and edit our maze with an image editor. Great solution, isn't it? I went ahead and already created an empty maze class that we're going to fill in. First off, let's leverage the pretty drawing syntax by inheriting it from SFDrawable. Unlike the entities of the game, the maze isn't transformable since it doesn't need to undergo changes, rotation, or even scaling. The graphic header has to be included as well. And any drawable object must override the draw method. We're going to do the job in 2 steps. First, we load the maze data by using the load-level method. Along with this method, we need the data structure of the maze. This is the maze size and a unidimensional array. And the second step is the rendering of the maze. To do that, we need a render texture. Each cell of the grid is either empty, a wall, a dot, a super dot, or a bonus. This enumeration will help us make our code more readable. We can now replace the integer with the cell data in our unidimensional array. Also, a constructor wouldn't hurt either. Let's get down to the implementation now. Create 3 methods implementation. The maze size is initialized with 0, 0. The load level function is where our image technique will rise to the challenge because with extreme ease, we'll be able to fill our maze data vector with the actual data of the maze. But before, let's have a look at the level I designed for this video. As expected, this is simply an image, very small because 1 pixel corresponds to 1 cell. That's why I zoomed in. This image is 15 pixels large to fit the entire area of the window, which is 460 pixels large. Given 1 cell is 32 pixels long, if we multiply 15 by 32, we get 480. Loading the level data consists of opening an image and reading its pixels one by one. If SFML fails to read the image, this is probably because it cannot find it. We'll raise a runtime error exception. The maze size simply is the image size. GetSize returns a vector using unsigned integer, However, we use regular integer. That's why I wrap the call around vector2i. And we cannot tolerate the maze size to be lower than 15 cells in both width and height. Otherwise, it's going to be smaller than the screen area. Then we're going to read the level image pixel after pixel. We usually do it row by row, and so we start with a for loop going from 0 to the height of the maze. Then we do the same for the width. Inside, we read the first pixel and retrieve its color. According to the color, we fill the maze data vector with the corresponding value. If the pixel is black, that means a wall. If the pixel is white, that means a dot. If it is green, this is a super dot. If this is blue, this is where Pac-Woman starts the level. It implies the cell is empty because the dot is somehow already eaten if Pac-Woman starts on it, right? And if the pixel is red, this is the initial position of one of the ghosts. This time it implies the cell contains a dot. Saving the initial position of Pac-Woman and the ghosts is important. So we're going to add two new attributes to the data structure: the initial position of Pac-Woman and a vector containing the initial position of ghosts. We also need accessors, and their implementations are indeed straightforward. Let's go back to the pixel color handling. When the pixel is blue, this is the Pac-Woman's position. We can save her position now. And when red, we add the ghost position to the vector. And voila! Believe it or not, we're done with reading the level data, and that was as simple as that. If we look at the result, the code is pretty concise, clean, and most importantly, readable. It would have been a pain to open a file, read character after character, discard empty spaces, interpret character delimiters, ignoring carriage returns, etc. Now, I'd like to bring your attention to how we naively added the cell data to the maze data vector. Our two-dimensional data is now packed in a one-dimensional array. Therefore, a common operation would be to convert the array index to the cell position, and the other way around too. It can be tedious to rewrite, and remember the formula, so let's implement two helpers: position to index and index to position. These functions can be made inline to be much faster, as they are just simple formulas that could be embedded as is. To compute the index from the position, we multiply the row index with the size of one row. Then add the column index. To compute the position from the index, declare a position vector. To get an x position, this is the index modulo the size of one row. And for the y position, this is the index divided by the size of one row. It might be confusing, but the math behind it is very simple. You can do it yourself by drawing a table and see how index and position can be converted to one to each other. The last function we need to implement is the draw function down here. Earlier we created a SF render texture, and this is on this texture that we are going to render the maze. Therefore, displaying the maze simply is displaying the internal texture using a sprite. Our job now is to render the maze on this render texture, and it takes place in the load level function just after we read the level data. First, we initialize the render texture with the size. The maze size in pixels is 32 multiplied by the number of cells in width and 32 multiplied by the height. This is because one cell is 32 pixels large square. Our maze has a uniform black background color. The first step is painting the whole texture in black. Then we are going to draw something on it, and at the end, we won't forget to finalize the drawing with the display method. This works just like a render window, in fact. To draw the maze, we're going to reiterate on each cell, but this time by using the unidirectional array. Then we convert the index to position using the function we wrote earlier. For now, we'll just draw one blue square for each wall, but later we'll enhance the visual. So we need a square shape, which we can create with SF rectangle shape. One wall is 32 pixels large, and its color is blue. Then for every cell, we draw that shape at the correct position. And that happens only if the cell data is a wall, of course. Now that the maze is rendered on that texture below, when displaying the internal texture, we'll get the expected result. But let's not forget to render the dots too. Instead of rendering on that texture, we will render them separately. This is because dots are going to disappear progressively as Pac-Woman eats them, and we don't want to redraw the whole maze every time one dot vanishes. To do that in the draw function, we will add the drawing logic of the dots. In a previous video, we modeled the dot entities. This was a circle shape we can retrieve by using getDots, and the super dots using getSuperDot. Also include dot.hpp header to call dot and super dots, and maze.hpp header as well. Again, we're going to reiterate the dot on each cell. We convert the index to the position. And if the cell data is a dot, we draw the dot in the correct position. I added +16 to position it at the center of the cell. And a similar code is found for the super dot. We are done with the rendering of the maze. The only thing left is using it in the playing game state. In the constructor, we load the level which is called level. Of course, we're going to work on adding more levels later, eventually replay the same level, but by increasing the speed. But the goal of this video is only about rendering the maze. And finally, let's not forget to draw the maze. It's time to check the result. The overall look is a bit rough because the border of each wall isn't rounded. But don't worry, we'll work on that in later videos. We can also see that one cell is empty. This cell is where Pac-Woman appears initially. Phew, that was a lot, wasn't it? We did so much. You deserve a pat for yourself. We created an entire maze. So we have accomplished our mission, which was to render the scene. In the next video, we're going to add the navigation logic. Starting from the next video, the game will start to finally become interesting. And much later again, we'll add more fun by enhancing the visual aspect and adding a camera to play on gigantic maps. In the previous video, we implemented the first version of our maze. We can see it rendered on our screen. Now our job is going to make Pac-Woman navigate on it logically. That means she has to collide with the walls and step in a row only when cells are free. That very same logic applies for the ghosts as well. This isn't going to be an easy part. We won't learn anything fun or exciting. Instead, we will do a lot of math to implement the required algorithms. As such, we're going to take a look at the logic that prevents characters from passing through walls. And then, take a look at the logic that allows a change in direction. Better take a theoretical look first, because implementing these algorithms won't be straightforward. So, we draw characters by telling their position in pixel coordinates. When we set the position at x, y, the image appears centered at that position because we changed its origin earlier. If we look at the maze, we notice several rows and columns where characters can be positioned. Our job is to restrict Pac-Woman and the ghost's position to these invisible lines. We'll be working with two variables, the current direction and the next direction. Both are two-dimensional vectors telling us four possible directions: left, right, top, or down. For instance, if Pac-Woman faces the north, the current direction value is 0, -1. The current direction is the direction Pac-Woman is moving toward, and the next direction is the requested direction. When the requested direction becomes available, the current direction is updated with this new direction. If we look even closer at each cell, we can notice that the cross represents where Pac-Woman should be positioned. Our algorithm is going to work with many values we have to pre-compute. And all these values are all related to the cell where Packwoman is currently on. To position Packwoman, we use pixel position or pixel coordinate. For instance, it could be position 152, 132. But we will also be interested in the cell position. Given our cells are 32 pixels big, we can compute the cell position by dividing it by 32. Later, we will want to work with that little cross inside the cell and work with a value named offset position, telling how far one point is from the center in pixels. The center is offset 0, 0. And as we move away from the center, the offset value changes. The offset value range from -16 to 16 on both axes. All these things aren't complicated in itself, but aren't intuitive and require us to do the math. So let's keep things simple and organized. Before we write any algorithm, we must first compute these three essential information pieces. Then once computed, it will be easier for us to implement the algorithm. The first thing we'll want to do is preventing characters from passing through walls. We're going to assume that Packwoman is already placed on this cross at a given offset. She could be here, or there, or even like that. At any time, Packwoman, she either faces the north, the west, the south, or the east. Preventing Packwoman from passing through a wall consists of 1. Checking if the cell in front of her is a wall, and 2. If the offset isn't greater than the given value. To get the cell position in front of her, we want to add the current direction to the current cell position. If that cell is a wall, we need to take action and eventually prevent Packwoman from stepping forward. Then, according to which direction Packwoman is moving towards, we want to check the offset value. For instance, in that scenario, Packwoman faces the east, and we want to check the x value. In that position, the x value is negative, but she will step forward, and later the position will become precisely 0. Then later again, the value will become positive. If the x value is positive in that case, we have to reset it to be 0. But the way we'll check the offset value is different. The second step is allowing change in direction. This time, instead of checking the cell in front of Packwoman, we will check the cell in the direction she wants to take. Adding the next direction to the current cell position will do the trick. If that cell is not a wall, and all the conditions are met to change the direction, we will replace the current direction value with the next direction value, so when the next frame is played, Packwoman steps forward in a new direction. We have to allow the change in direction only when Packwoman is close to the intersection. To do that, we can check the offset value to be within -2 and 2, for instance. That's enough for the theoretical part. Let's get implementing those algorithms now. In fact, the logic we just saw for Packwoman applies to ghosts too. Thus, it makes sense we implement it in the character class. At every tick, we're going to call the update method. I made it virtual because other logic specific to each character will follow. Like we said, we will work with two direction values. The first is current direction, and the second one is next direction. To change the character direction, we're going to call setDirection method. And we can also retrieve the current direction. Be careful with their implementation. Setting the direction must go in the next direction variable. This is because a change in direction is applied only when the character can actually change its direction. And the getDirection method returns the current direction. Down there, we have the update method in which most of our code will go. For instance, we're going to perform that change in direction by writing m underscore current direction equals m underscore next direction. But I will comment it out because we need to implement the conditions first. Let's also not forget to initialize the attributes. Actually, in the update method, we will also need an access to the maze instance. We will quickly fix that by adding setMaze method and set their implementation. Also include maze.hpp header and set their implementation. Now it's time to actually create the characters. There's only one Pac-Woman, but there are more than one ghost. And we will comment out the line which is not needed. Initialize Pac-Woman instance, and again, comment out the line which is not required now. Just after the maze is loaded, we can create Pac-Woman. Comment out the line which is not required now. She needs the texture to set up her visual and also be set up with the maze instance. At the beginning, she is positioned on a given cell of the maze, which we can retrieve by calling getPacWomanPosition. But this returns the position in cell coordinate when we need it in pixel coordinate. That's why we're going to make a quick detour and implement two important convenient methods in the maze class. Map pixel to cell position and map cell to pixel position. To convert a pixel position to its corresponding cell position, just divide it by 32, since our cells are 32 pixels large. However, to convert a cell position to its pixel position, we have to multiply it by 32. We will also add 16, so the returned pixel position is actually the center of the cell and not the left upper corner of the cell. Now we can go back to the creation of our characters and move Pac-Woman to its initial position. Creating ghosts isn't any more complicated. This time, we will iterate over each ghost position and create ghosts one by one. We have created many characters using the new operator. We also have to delete them, and it takes place in the destructor which we need to add by the way. The final touch is to call their update method. And forward the elapsed time because they also need to be aware of the time going by. Then draw them. We need to shift this line above as we want to draw our maze first. Here, I have commented out some code that is not required, like the animation we did in the playing state, the weak method, and our Packwoman files, and the initial positions that are required as well as the ghosts. You can also comment out this line. And then, save all the files. If we run the code, we can see each character drawn at their initial positions. Now these characters have to move. To do that, at each frame in their update method, we have to slightly change their position. We can start with retrieving the current pixel position. Then we can compute the number of pixels she traveled on one axis in one frame. The speed is expressed in pixels per second, so we have to multiply it by the number of seconds that has elapsed. Next, we can say the next pixel position is the result of the current position plus the current direction multiplied by the number of pixels traveled. When a vector is multiplied by a scalar, each component of the vector is multiplied by this scalar value, and this results in another vector. Given the current direction is normalized, that means value are either -1, 0, or 1. Their multiplication will either make the number of pixels traveled negative, 0, or keep it positive. If you don't quite understand this code, I invite you to take a sheet of paper and do the math yourself. Oh, and I forgot to convert the current direction variable to a floating vector. And then, we can change the position to the new next pixel position. We agreed we would also pre-compute the cell position. So far, we have the pixel position up here. Now let's compute the cell position. And finally, the offset value. We have to modulo the pixel position with 32 and subtract 16. The math behind this isn't complicated, and I invite you one more time to do the math yourself. Pixel position module 32 will result in a value between 0 and 32, but we need a value between -16 and 16. That's why we subtract 16. Now these three essential values are computed, we can move on and easily implement the logic that prevents the character from passing through the wall. we have to check if the cell in front of the character is a wall or not. To do that, we could ask the maze instance if a given cell is a wall, and it would return either true or false. We haven't implemented this method yet, so let's do it. The maze data attribute is a unidirectional array, so we have to convert the cell position to its index. Then we simply check if the value at this index is a wall or not. Additionally, we will also check if the position is within the maze bounds. If it's not, we can return false to say it's a wall. Back to our algorithm, we can continue and say that if there's a wall in front of Pac-Woman, we need to reset Pac-Woman position to be centered on that cell. And this is only if she went too far. To reset, we can write this code. Map cell to pixel will return the center of one cell in pixel coordinate. And finally, to check if Pac-Woman went too far, we can check the offset value according to the current direction. If the x value of the current direction is 1, then that means she is facing the east, and we have to ensure the offset value isn't positive. However, if the x value is -1, then that means she is facing the west. In that case, the offset value cannot be negative. And finally, the same code applies on the y-axis. That piece of code is scary, but gathers in 4 lines all the conditions to detect if there's a collision. With a good understanding of the meaning of the offset value, it makes life much simpler. That code prevents one character from passing through a wall. Next, that very same character could want to change its direction. That's why we're going to check this time for wall in the eventual next direction. This code runs only if the next direction is different from the current direction. And eventually, if the conditions are met, we're going to find this code we commented out earlier. These conditions are: if the character is close enough to the intersection, we allow that change. Again, this has to do with the offset value. So I can detect if Pac-Woman is moving on the x-axis by checking the y component of the current direction. y will be 0, and this condition will be true. When Pac-Woman moves along the x-axis, we need to ensure the offset value in horizontal is close to 0. By writing this code, we ensure it is between -2 and 2. We have the code for the y-axis. That's it. We can allow a direction change when those two conditions are met. Importantly, we also have to recenter the character on the current cell. Think about it. Pac-Woman might not be perfectly centered when the change in direction is allowed, and in that case, she will be misplaced. We can achieve that by resetting Pac-Woman's position on her current cell. We can fix that by applying a transformation to its sprite. To be short, according to the current direction, we apply the corresponding rotation and/or flip the image horizontally. For instance, when she looks leftward, no rotation should be applied, and we have to flip the image. However, when she looks downward, the rotation is needed and the horizontal flip. And so on. Now we are getting the result we want. Enjoy! We finished implementing the hardest part of our game. You should be happy if you understood everything after a first view. But if there are unclear points, just keep watching again and practicing until you get it. This is actually easy to an advanced programmer, and one day you'll be able to do all these basic math operations without thinking too hard. Working with normalized values, multiplying vectors together, computing things according to the speed, etc. You master all these things when working on bigger projects. In the meantime, enjoy the result and see you in the next video. In the previous video, we reached a state where we could already move Pac-Woman in a working maze. But we won't stop just yet. We'll keep working on the maze. In this video, we will enhance the visual of the maze by rounding up the edges of the maze. We are going to look further at the geometrical transformations we can apply to drawable objects. First, we are going to take a look at working with the origin. Then, we will apply the three fundamental transformations, which are scale, rotation, and translation. Those are often shortened as SRT. Until now, each wall of the maze is just a 32-pixel large blue square, and the overall look is a bit rough, and we would like something smoother, more appealing. That's why we are going to round up the edges and corners to get the following result. To do that, when each cell is drawn one by one, we will customize the rendering according to the cells that surround one wall. And that will be done using three small images. The first one is the border image. Then we will work with the inner corner image, and finally the outer corner image. This is all we need to do the job. By drawing these three images more than once with different transformations, we'll be able to build up a complex wall cell like this one. We'll do that in 3 steps. Step 1. We'll start with drawing borders. At the beginning, the entire cell is drawn in blue to represent a fully drawn wall. This is the starting point of our drawing algorithm. We are going to check the adjacent walls one by one to check whether they are walls or just empty spaces. If the adjacent cell is empty, then we can draw a border. For instance, if there's a wall on the right, we can draw a border like that. If there's a wall on the top, we will draw a border like that, and so on in the 4 directions. Eventually, we will end up with more than one border drawn like that. But that's fine, because we're going to take care of drawing the corner in the next steps, which will overlap this ugly incoherence. Step 2. Drawing the inner corners. We're going to draw an inner corner when the 2 adjacent cells related to this corner are walls. And the same logic applies for each corner. Step 3. The drawing of our outer corners. This is actually the same logic, but unlike step 2, we're going to check for empty walls. So if the cell on the top and the cell on the right are empty, we can draw an outer corner. To draw these images, we need to change their transformation origin. By default, origins are on the left upper corner of images, but we want to change them to there. This way, when we apply rotation, each image rotates around this origin and borders itself correctly. It's not that complicated, but it can sometimes be painful to visualize this. Anyway, now we have the strategy in mind, let's implement it. The new drawing logic takes place in the maze load level method. Remember, we pre-draw the maze in a render texture. First, we need to access the assets texture so we can use the border and corner images and customize the rendering. Let's not forget to modify the game state to construct the maze with the assets texture. Here we go. So now in the load level method, we can create 3 sprites for each image. We need to set them up, both the texture rectangle and the origin. I invite you to open the assets image with an image editor such as GIMP to understand better the values I'm putting here. Along with these changes, I'm also changing the origin, which is really important to apply rotation later. Then down here, for each cell which is a wall, we will add more rendering logic. First off, we can replace this bit of code with the isWall function we wrote in the previous video. This function has the advantage of handling incorrect coordinate positions. For example, if the position I'm passing here is negative, like -1, -1, it will return yes because an out-of-grid cell should be considered as a wall. So when the cell is a wall, we can modify our 3 image positions by using map cell to position. Step 1 is drawing borders. So if the wall on the right is empty, then set rotation to 0 and draw the border image on the render texture. The same applies for the 3 other borders. And the difference is the rotation applied, which has to be increased by 90 degrees. Step 2 is the inner corner. We have to check if the 2 adjacent cells are walls. And if they are, we will draw the inner corner. The same applies for the 3 other corners. The difference is the rotation. And finally, the outer corner. This is exactly the same logic, so I can start with duplicating the code. Then, instead of checking for wall, we can check for empty cells. And instead of drawing the inner corner, we draw the outer corner. The code which we replaced earlier for if condition that we will write here for the wall. If we compile and run the code, we should get the promised result. Mission accomplished. We have successfully smoothed out the walls of our maze. The overall look is much better and smoother now, and we should be happy with that. In the next video, we will add a camera. Until now, the maze is quite small, and collecting all the dots is a matter of seconds. We need a longer game experience for our players. To work around that, we will enlarge the mazes and add a camera to track Pac-Woman's position as she runs throughout gigantic mazes. See you in the next video. In the previous video, we rounded up the corner of each wall to improve the overall visual and get a smoother look of the maze. In this video, we're going to add a camera in order to play on mazes much bigger than the window area. To accomplish this mission, we will study something new in SFML, the concept of view. Once understood, we will go ahead and use views to implement a camera-like feature that tracks Pac-Woman's position. In SFML, we use pixel coordinates to draw objects on the screen, and these coordinates are always related to the upper left corner of the window. That means the upper left corner is 0, 0. Indeed, objects drawn outside of this window area don't show up on the screen or show up partially like the orange rectangle on the right. In fact, the window is just a container to display the image of the game, but what actually defines what is drawn on this window is a view. A view can be seen as a rectangle, which is initially as big as the window, and all objects drawn inside the view area will appear on the window. But unlike the window, this view can shrink, grow, and even rotate. And no matter how this view is set up, SFML will map its content to the window area. Let's have a look at an example. If we make this view bigger like that, more objects are likely to be inside the view area. For instance, now we have the orange rectangle fully inside the view area. As a consequence, we'll be getting the window with all objects contained in it. Indeed, all objects are shrunk to fit inside the window area. Pause few secs. Now, if we were to move the view around like that, each object would move accordingly on the window side. Pause few secs. This is how we implement a camera-like feature in SFML. Now that we understand the concept of view, let's move on to the View API. You don't need to go too far for that. All the documentation is available on the website. View objects are from the SF::View class, and they work tightly with the window class. The three methods in front of you are from the Windows class. They enable us to modify the view of the window, change it, and get the default view. The default view is the one that doesn't affect the object visuals at drawing time. If you want to create a custom view, you should construct it from its center and its size. First, you tell the view how big it is. Let's suppose 640/480 for this view. Then, you'd tell the camera where to point at by specifying its center. By default, the center is half the size of the window. Then, once created, you have access to various methods to move around the view, rotate it, or even zoom it. Zooming in or out is nothing more than resizing the view, by the way. For this video, I have prepared a whole new level image, which I named Large Level. No surprise, this is just an image, but much larger this time. Since one pixel corresponds to one cell, we need to zoom in a lot to get a decent overview. The goal of this video will be to play on that maze. Let's start with modifying the loaded level in the game state. Next, we will add a custom view to the game state. Its name is Camera. This camera needs to be set up, and we want it to be as big as the window. At every moment of the game, this camera has to be centered on Pac-Woman, but Pac-Woman always moves. No problem. We can center the camera at every frame in the update function down here. Now let's apply the camera by changing the view of the window. And that happens just before we draw anything on it. Let's check the result. The camera properly tracks Pac-Woman's position, but it goes outside of the maze, which is undesirable. What would be great is when we reach the border of the maze, it doesn't show the outside. Let's check on the other side to see how it does the same. Again, we see the result is unpleasant. So let's fix that. It's quite easy, actually. We're going to solve that problem by recentering the camera when the center value is incorrect. This takes place just after the camera center is updated. If the camera position on the x-axis is less than half the window, that means we reach the left border. So we will force the value to be half the window. The very same code is found for the y-axis. We also need to recenter the camera when we reach the right border of the maze. The value to work with is the size of the maze in pixels subtracted by half the window. The camera center value cannot exceed this size. To compute the maze size, we have to reopen the maze files, and add a function getSize. This function returns how large the maze is in cells, not pixels. So we have to be careful to multiply this value by 32 later. Now we can finish the implementation. When the camera center is greater than the maze size multiplied by 32, subtracted by 240, recenter it. The same for the y-axis. Voila! Let's check the result one more time. This time, the camera doesn't show the outside of the maze. Let's check the other side to be sure. Aye, it works like a charm. Implementing this camera feature wasn't that hard finally. Thank you to SFML for this awesome feature, which is View. We're definitely done with the maze. In this section, we created and edited gigantic mazes and implemented the logic to efficiently render them. We made our characters move logically on this maze and ended up adding the most advanced feature of our game, a camera that tracks Pac-Woman's position. In the next section, we're going to implement the gameplay. This will involve working with artificial intelligence to implement realistic moves of the ghosts. Then, we'll tweak our code to play different levels with difficulties, compute score, implement bonus, and much more. I look forward to seeing you in the next section. Bye-bye. Hi and welcome to the last section, adding the gameplay. For some of us, this is the most interesting section because the gameplay actually shapes the fun of the game. But to me, this is the less interesting part because this is a creative part and I'm not good at that. But don't worry, we'll drive that game to the finish together. To have an interesting gameplay, we need the enemies to move intelligently. We're going to take a look at writing artificial intelligences. Then, we want Pac-Woman to collect dots and super dots as she runs through the maze, so we'll be implementing the logic to collect these objects in the maze. Along the way, we'll also implement the apparition of bonus. Later, we'll take a look at the implementation of the graphical user interface. Something really minimalistic to display, the current level, the number of remaining dots, etc. We're also going to take a look at adding the levels and the score, because what would the game be without it? This section starts out with the most difficult step in implementing the gameplay, writing the artificial intelligence, or we can also shortcut it and say AI. So far, we have created the ghosts that are motionless, but they should move in order to seek and catch Pac-Woman. This is to prevent the players from completing the levels too easily, and also to make the whole game challenging and interesting. That's why in this video, we're going to have a quick introductory on artificial intelligence. Unfortunately, artificial intelligence is a very big topic, complicated, and actually has its own field in computer science. It goes way beyond the scope of these video tutorials. That's why we're going to make it simple and implement AI by computing and comparing angles only. With that technique, we can quite easily implement a seek and catch AI and an avoid and run away AI when the ghosts are vulnerable. Like I said, artificial intelligence is a very complex topic, and we can actually find specialists out there who spend their entire career writing and researching artificial intelligence. Of course, we are not expert, but we should at least know the rudimentary. To understand artificial intelligence, let's analyze first what happens in our brains in the following scenario. Obviously, we see that the harmful ghost is near us, and the only way not to get caught is to move right, then either go up or down. Quickly, we're able to make a decision according to the environment. The artificial intelligence is the logic that substitutes our brain and make these decisions. Concretely, this is just a bunch of logic found in one function that takes the entity and the scene in parameters. The entity instance is to change the entity behavior, like changing the direction. For instance, if the entity is a ghost, then by changing his direction, we change his behavior. And it also takes the scene instance to inspect the environment and make the decision according to it. As a player, we see the screen, and according to what we see, we make decisions. Well, the computer doesn't have eyes, and instead use the scene to get the information seen on the screen. The question now is, what to write in this function? Well, While our brain is able to make decisions and we can vaguely explain why, our machine are just computing machines that need very precise instructions, and this is where all the complexity of that field lies. The purpose of the ghost is to kill and prevent Pac-Woman from catching all the dots, and for that, we could come up with thousands of strategy. For such a simple game, a usual solution would be to perform pathfinding algorithms. According to the 2D grid, what is the shortest path to reach Pac-Woman? Or even, according to the other ghost positions, coordinates their actions to trap Pac-Woman. But those are already very advanced algorithms, and for our tiny game, we're going to work with computing angles. We're going to say, according to the angle formed by the position of one ghost and Pac-Woman, select the closest available direction. Let me explain. In this scenario, computing the angle between Pac-Woman and this ghost results in a value close to 90 degrees. In this case, around 110 degrees. 110 degrees is closer to the top direction than the three others. So the best decision made based on that angle is the top direction. However, we also notice the top direction isn't available. There isn't any row in which the ghost can step in. In these cases, ghosts shouldn't fall back on the second best direction, which is here left. In fact, we will maintain a list ordered from the best direction to the worst direction. To change the direction, we will simply iterate over this list until it matches an available direction. To implement the runaway behavior for when the ghost is vulnerable, we will simply reverse the list and proceed with the same algorithm, but backwards. The last thing to understand is when to call this function. We will call it decision time. Ghosts should update their direction regularly, but not too often. To do that, we're going to execute the artificial intelligence function only when there's a change in the available direction. For instance, in this scenario, the ghost is moving toward the top and should make a decision when the row on the left is available. If he chooses left, the next decision time will be at this next intersection. To detect when these ghosts reach these intersections, we're going to check every time they move to the next cell if the available directions are the same. When there's a change in the available directions, the AI function has to be called. While it's fresh in our heads, let's start with detecting these decision times. Let's open character.hpp file and add previous intersection. This one is going to retain the previous intersection cell position. And we also need an array of Boolean. This one remembers the availability of the fourth direction. Later, we're going to compare it with the current available directions, and if the two values are different, the function changeDirection is called. By default, it does nothing. That's why I added some brackets with nothing inside. We can initialize the previous intersection attribute within 0, 0. Next, in the update method, we can compute the available directions. The code is long and tedious, so let me copy and paste it. It starts with maintaining a list of the fourth direction. The overall algorithm consists of checking if the next cell has the same available directions. So only if the cell position is different from the previous intersection, we perform the checking. We need to furthermore investigate the exact position to see if it's within 2 pixels from the center. Then we can finally start the checking. We declare the exact same array of Boolean to retain direction availability of the current cell. Then, according to the current cell, we detect the availability of each direction one by one. This is done by calling the isWall method. Now we can compare it to the previous availability. If it's changed, then we call changeDirection. And indeed, we update the previous intersection as being the current cell position and the available directions. From now on, the changeDirection method is called in our Ghost class, so we can move on to its implementation. So in this function, we need to implement the artificial intelligence, or AI. And for that, we need to know where Packwoman is. Let's add a pointer to Packwoman as attribute. Along, we modify the constructor. We also need to pass the argument when creating the ghosts. This is done in GameState.cpp. Now the real work begins. This is going to be tough, so listen carefully. The first part of the algorithm is to compute a sorted list of directions that goes from the best direction to reach Packwoman to the worst direction, as we saw earlier in the theoretical part of this video. For this, we have the std::map container. This container saves the angle difference and the associated direction for which it has been computed. So let's imagine we start with working with the top direction. The top direction has an angle of 90 degrees. Then we compute how far the angle formed by Packwoman is from 90 degrees. If the angle is 110 degrees, the difference with the top is 20 degrees because we need 20 degrees to reach 90 degrees. The same if the angle is 70 degrees, we would also get 20 degrees because we need 20 to reach 90. We are going to do that for the fourth, and that's what this container is for. By the way, we need one more time a list of the fourth direction. Now we're prepared to write the algorithm. We need to compute the angle, so let's call it target angle. We first need the distance of Packwoman from the ghost. This is the result of Packwoman's position subtracted by the ghost position. With that distance, we can use std::atan2 to retrieve the angle in radian. Until now, I kept using degrees because people are usually more familiar with it. However, radians present interesting properties that facilitate some arithmetic operations. That's why the STL library expect radians. That's not a big deal. We can easily convert it to degrees by multiplying it by 180 divided by pi. So this is the target angle. Now let's compare it with the fourth direction. We need to compute the direction angle. Again, we can use atan2, and we also convert it to degrees. The next difficulty is that the very same angle can be represented in different degrees. Think about it. An angle of 330 degrees could also be minus 30 degrees as well. Both are different numbers, but they still represent the same angle. That's why we need to what we call normalize the angle so that it results in a degree in the range of 0 and 180. We start with subtracting the direction angle from the target angle to get the difference. That's actually the angle we want to normalize. So the result of this can be either positive or negative. That's why we need the absolute value. But yet, this value can be higher than 180 degrees, so we're going to remove 180 degrees from it. In some scenarios, it can result in a negative value, so we need the absolute value again. Now we are sure to have a value between 0 and 180. And finally, earlier we removed 180, so we need to remove somehow the same amount. This time we're going to do 180 minus what we got. Now our angle value is normalized and is ready to be compared. We can add it to our map container. And this process is repeated for the three other directions. At this point, we have very good news. The associative contained standard : map is already sorted by the key values. The associative contain std::map is already sorted by the key values. That means if we iterate over each key value pair, we get the best direction first and the worst ones are at the end. Now we could simply write set direction prob.begin second. But remember, the best direction isn't always available. We need to fall back on the best available direction. To do that, we will write we get an iterator, then we change the direction to the best direction. We increment the iterator, and we stick with that direction only if the ghost will not move if we leave as is. Of course, we haven't implemented will move yet, but the logic is there. We try one by one from the best direction to the worst one if the ghost is going to move. When the ghost is moving, we keep that direction, and once the artificial intelligence finishes its work, the ghost gets the next direction information. After this, we will add a pointer of Packwoman and update the character in the update method. Let's implement will move now. Will move is actually simple. We check if the previous intersection plus the next direction results in a wall. So if we recall the algorithm, it's going to check direction after direction. So when this code results in a wall being free, we know that the character will move. We will also include an array header in the character.hpp file. Okay, done now. If we run the code, we should get our ghosts moving around according to Packwoman's position. Voila! Mission accomplished. The result is a little bit primitive, but it works. In the next video, we're going to collect dots and bonuses. Like you could see, we can move and even ghosts now can move, but we're not collecting dots when we go past them. The next video is going to implement these logics. In the previous video, we wrote a very simple artificial intelligence for the ghosts. In this video, we will continue adding the gameplay by making Packwoman collecting dots and bonuses. In fact, in this video, we'll go a little beyond collecting dots and bonuses. We will also talk about collision of Packwoman with ghosts. This is because collecting dots and bonuses has to do with collisions. So we are going to take a look at detecting collisions. Along the way, we will also implement the apparition of bonuses. Even though collecting dots and bonuses also involves collisions, we won't implement it the same way we do for monsters. Let's understand how we are going to detect collisions with dots, superdots, and bonuses first. We will call them objects. At every frame, Packwoman and ghosts are slightly moved to stimulate a continuous movement throughout the maze, and collisions with objects can happen at any time. That's why our detection code will go to the update methods. And to detect collisions, we will reuse the cell position and the offset value. We will detect on which cell Packwoman is, and if Packwoman is close to the intersection, we will eventually process the collecting by calling pickObject from the maze instance. Checking if Packwoman is close to the intersection is the same as checking if the offset value is within a short range, such as 3 pixels. However, to collide with ghosts, we are going to use the technique, the collision box. For each visual appearing on the screen, ghosts, Packwoman, dots, bonuses, we could define virtual rectangle being the smallest rectangle containing that visual. In graphics computing, we call that the bounding box. The bounding box in 2D is merely a rectangle which can be represented by the SF::rect class in SFML. As this relates to pixels, we parameterize it with the float type. And a shortcut would be to write SF::float_rect. Luckily, we don't even have to write the collision formula because SFML provides a method intersect that returns either true or false. For instance, we can write bounding box A dot intersects open bracket bounding box B close bracket. When the two bounding boxes don't intersect, we'll get false. However, when they do, we'll get true. Also, for a nicer result, we'll shrink a little this bounding box. We are now ready to implement our two types of collisions. If you recall the global architecture, we split the logic of our game into 5 game states. Our code is going to take place in the update method of the playing state because it holds an instance of the maze, Pac-Woman and the ghosts. So we need to work with the offset value. Let's quickly recompute it. We first need the pixel position of Pac-Woman. Then modulo 32 subtracted by 16. Then, if Pac-Woman is close to the intersection, let's say within 3 pixels from the center of the cell, we compute the cell position from the pixel position. Then, according to the content of this cell, we will take different actions. For instance, if that's a super dot, we will make every monster vulnerable. Then, later we will pick the corresponding object. Let's have a quick detour in the maze instance because we need to implement these two methods, pick object and isSuperdot. IsSuperdot returns a Boolean and takes the cell position in parameter, and pickDot only the cell position in parameter. Why not also implement isBonus method? We'll need it later. To tell whether one cell contains a superdot or not, we have to check the maze data instance. As we've used a unidimensional array to store our two-dimensional data, we have to convert the cell position to the index using position to index. And finally, check the value against the superdot enumeration value. The isBonus is actually the same, but instead of checking against the superdot, we change it to bonus. PickObject method consists of modifying the cell data to empty. To prevent any logical error, let's add an assert statement to ensure this method is never called when the cell is a wall. A wall never contains any object. We will add a header for this as well. We can go back and finish the implementation. When the object is a superdot, all ghosts become vulnerable for 5 seconds. Let's move on with the collision with ghosts. Back to the playing state. At every frame, Pac-Woman might collide with a ghost. So we are going to iterate over each ghost. Then, if Pac-Woman bounding box collides with the ghost bounding box, 2 things can happen. If the ghost is vulnerable, the ghost dies. Otherwise, Pac-Woman dies. To kill the ghost, we simply remove it from the list. And to kill Pac-Woman, we will kill her with die method. But unlike Ghost, Pac-Woman plays a dying animation and revive after it. That's why we're going to check for when she really is dead and reset her. Resetting Pac-Woman is putting her back to the running state. Let's implement that now. She's not dying anymore, nor dead. And we can rerun the run animator and update her visual immediately after. We will define the bounding function that we have used for collisions in the character.hpp and character.cpp files. Let's go ahead and implement it now. Now, once reset, Pac-Woman and ghosts have to be put back to their initial position. We already wrote the code for that, and we don't want to duplicate it. That's why we are going to create a move characters to initial position function and paste the same code. This will set the character to its initial position. And finally, we have to reset the camera position to focus Pac-Woman's new position. We also already wrote this code again. We're going to externalize it and write update camera position. Now in the update method, we will update the camera and the character's initial position. Let's check the result. The dots are properly taken. When I take a super dot, ghosts become vulnerable. Check. Let's see if I can kill them. Perfect. And now, let's see if they can kill me. Okay, cool. let's move on to the next video. In this video, we have implemented the collecting of dots, super dots, as well as the killing of either Pac-Woman or Ghost when they collide. In the next video, we will add what we call HUD. It's a tiny graphical user interface to display useful information like the score, the current level, how many lives left do we have, etc. It's going to be one big step towards a finished game. Stay tuned and see you in the next video. In this video, we're going to implement the graphical user interface of our game, also called HUD in our case because our interface is minimalist. But I'm going to go into details in a few secs. So, to display the HUD of our game, we'll need to have a look at rendering on SF::render texture. I guess for some of you, HUD is a new term, and explaining that explanation is appropriate. I propose to have a look at a screenshot of the original Pac-Man game and see where the HUD is. At the bottom of this image, we can see the scores displayed. Then next to it, we have how many lives left the player has. And on the right, we have a cherry image. Honestly, I don't know what this is about. Maybe to indicate a bonus is going to appear on the screen or something. Nevertheless, these three things are called heads-up display and give useful information to the player. It's not part of the scene and are clearly independent objects with no relation with the scene itself. In our game, we're going to add two more heads-up display, one telling how many dots are left Pac-Woman has to pick up, and the level being played. When we look at our game, we have an issue, because we have no space left to display the HUD. That's why we're going to make our window slightly bigger on the y-axis. Instead of being 480 over 480 pixels, it's going to be 480 over 500 pixels. It will leave us with a little space at the bottom where we can display the HUD of our Pac-Woman game. It makes sense we start with making that window bigger. So instead of having 480 pixels in height, we have 500 pixels. In the playing state, we have a new render texture named Scene. This render texture has to be created, 480 over 480 pixels. Now we are going to slightly modify the drawing algorithm to render everything, maze plus characters on the scene render texture. It consists of replacing each window instance with m_scene. Then, once finished, we call display to finalize the rendering. And draw the scene back to the window by using SF::sprite. Now the scene should occupy only 480 pixels in height. We can also notice the additional space at the bottom. We can move on the next step, which is actually displaying the HUD. We are going to need a text to display the score, another one for the level, also one for the remaining dots, and finally, 3 images representing the 3 lives. The 3 texts have to be set up with the font. The character size is going to be 10 for the 3. However, their position will vary. The score is displayed at position 10, 480, and we can display a temporary text 0 points. The level is positioned at 160, 480, and it's going to be level XY. Finally, the remaining dot text is 280, 480, and can contain text 0 dots. The 3 lives image have to be set up with the texture. And the texture rectangle is 122, 0, 20, 20. The only thing that differ is their position. About 20 pixels separated from each other. Lastly, we won't forget to actually draw the HUD. That little 3 here is going to be replaced by the actual number of remaining lives. Let's have a quick look at what we get. It looks really nice so far. But there's still one thing that bothers me. Let's restart the game. When the game is at the Get Ready state, it would be great if we could get the scene displayed behind, too. We are going to work around that by displaying the playing state in the Get Ready state. So we add a pointer on the playing state in the Get Ready game state. And in the Draw method of Get Ready state, we can draw the game. That way we can easily enhance the overall look of the game. So let's not forget to initialize this instance. After this, we will modify the Update method in our Get Ready state. This should get us the correct result. In this video, we have implemented a tiny graphical user interface for our game that consisted of a few texts and images telling the player useful information on the game state. But these useful informations aren't updated yet because we still have to work on the gameplay itself. That's why in the next video, we will actually implement the level workflow, compute score, and tons of other stuff. See you in the next video. In the previous video, we implemented a minimalistic user interface and made some space to display useful information like the current level or score, or even the remaining lives. But this information isn't updated yet because we haven't implemented the level flow and the computing of the score, etc. In this video, we're going to implement these remaining pieces of our game and update the user interface accordingly. We're going to take a look at an interesting level progression for our game. Then, during the progression of the game, the score must be computed. For instance, when Pac-Woman collects a dot, it gets 10 points. Of course, Pac-Woman shouldn't have an unlimited number of lives. After 3 deaths, the game is over. I designed 3 levels, each a little bigger than the previous level. We could implement more levels, but for our game, I decided to limit it to 3 only. I placed these images in the Assets directory and called them respectively small.png, medium.png, and large.png. The player is going to rotate on these mazes, and every time it goes back to the first maze, the speed will slightly increase. We're going to represent the current level with 2 numbers. The first telling how many times the player passed these 3 mazes, and the second is a number between 1 and 3, telling which is the current maze playing. For instance, the first level is 0, 1, and we play on the small maze with speed 50. Then once completed, the second level becomes 0, 2, and we play on the medium maze, but still with the speed. Next is 0, 3, and we play on the large maze. Then we go back on the first small maze, but the speed is increased to 75. The level is 1, 1. Unlike the levels flow, the score flow is easier to understand. We start with 0 points, and anytime we collect a dot, 5 points get added. A super dot, 25 points. But catching a ghost increases the score count. We get 100 by killing a ghost. And finally, a bonus is 500 points worth. We have quite a large amount of stuff to implement. We're going to start with implementing the level workflow. So every time the player completes a level by picking up all the dots in the maze, we will call a method loadNextLevel. This method is going to work with a variable level. Let's also initialize it to 0. Until now, when the playing state is created, one maze is loaded by default. This was done by calling loadLevel from the maze instance. We will let the newly loadNextLevel method take care of loading the corresponding level. So, cut. And down below, we create that new method. And we paste. The loadNextLevel method role is to load the next level, so it starts with incrementing the level variable. Then, according to the new value, it loads the appropriate level. At the beginning of this video, I explained the workflow. Every 3 levels, we go back to the first level, so level module 3 will result in a number between 0 and 2. Later, according to how many times we played these 3 levels, the speed will increase. We can compute the speed level by dividing the level by 3. Now, according to the map level variable, we can load either the small level when the value is 0, the medium level when the value is 1, and the large level when the value is 2. After loading the level, we have to create the corresponding characters, change their speed according to the new level, and finally move them to their initial positions. This method will be called more than once, so we have to erase previous characters first. Unlike ghosts, Pac-Woman is created once and for all, so we don't have to erase her. Then we can recreate the ghosts. Actually, we already wrote that code up here, so we can just cut and paste it. After that, we must change the character speed according to the speed level variable. We're going to say the initial speed is 100 plus the speed level multiplied by 50. In other words, every 3 levels, we increase the speed by 50 pixels per second. Pac-Woman is going to be slightly faster than ghosts by 25 pixels per second. And we can change the speed of each ghost. The very last step is to move every character, Pac-Woman and ghosts, to their initial position. We might think we're done, but actually, we need to make a minor modification to the loadLevel method in Maze. When we wrote this function, we didn't anticipate we might call it more than once. So anytime we load a level, we clear the previous data. It consists of clearing the cells vector and also clearing the initial character positions. If we didn't do that, calling many times this function would have stacked the previous level data again and again. While we were working on the Maze class, let's implement getRemainingDots method, a function we'll need shortly to know when the player actually passed the level. To know how many dots the player has to take, we need to iterate over each cell. So we're going to start with a local variable, RemainingDots, initialized at 0. The cell by cell, if the content is dot or superdot, we increment the remaining dot variable. And then we return that value. Now in the playing state, we can detect when the player won the game by writing if maze.getRemainingDots is 0, we can call loadNextLevel. But if you recall the game state workflow, once the player wins, the won game state becomes active. So we are going to delegate the work to the won game state. Instead, we will change the game state to one game state. If players can win, they can also lose. They lose when Pac-Woman dies. We can detect that up here. If Pac-Woman is dead, then we change the game state to lost game state. Both won and lost game states are going to perform different actions. For instance, the won game state we'll call load next level, and the lost game state we'll call reset to 0, or reset live count when the player spends his money to keep playing. We will also need reset current level. To call these four methods, these game states need an access to the playing state instance. So we will pass the playing game state instance to their constructor. I used the base game state class, so we need to cast it to the concrete playing game state class. And finally, pass the instance at creation time. Now our game states can perform actions. In the one game state, after 5 seconds, the next level has to be loaded. Then the following line will change the game state to the get ready state. The lost game state has to reset the game if the player hasn't inserted a coin within 10 seconds. However, if the player does, it has to reset the current level, and also reset the live count, so the player has 3 more chances to go further in his score. The only thing left is implementing these 3 new methods. Let's start with the easiest one, reset live count. To reset the live count, we actually need a live count variable to work with, and that one gets initialized at 3. Resetting the live count simply is modifying its value. To reset the current level, we're going to use a little trick. We start with decrementing the level variable, and simply call the load next level method. That way we don't have to care about the internal details. Resetting the game to 0 consists of resetting the live count, setting the level at 0, and call reset current level. Now that we have implemented the live count, we can decrease that number every time Pac-Woman dies. And the game jumps to the lost mode only if the value is lower than 0. Otherwise, we adjust each character to their initial position. We're finished with implementing the levels flow. Up here, we can write reset to 0 method. Let's move on with implementing the score flow now. We need a variable score for that, initialized at 0. In the update method, we can detect when the cell position contains a dot by typing maze dot is dot, open bracket, cell position, close bracket. And we increase the score by 5 points. This method isn't implemented yet. This function is similar to all others, isWall, isSuperdot. And the implementation is similar too. Instead of checking for a superdot, we check for a dot. We can continue in the update function. When the object is a superdot, we increase the score by 25 points. If this is a bonus, we increase it by 500 points. Down there, we can detect when a ghost dies, and we increase the score by 100. That's pretty much everything for the score. We just don't have to forget to reset the score to 0 when we reset the game. We're actually done with the most important part of the gameplay. There are only details left, like we have to update the HUD accordingly. At the very bottom of the update function, we can update the score text. And we do the same for the remaining dots. To update the level text, we need to go to the Load Next Level function, where we have access to the current level variable to update the text. And finally, there's only the live count HUD to update. Instead of displaying 3 image, we will display according to the actual number of lives left. Now we can erase the initial texts in the constructor. Voila! I think we're ready for a small test. So let's compile everything and run the game. We can notice that the score is correctly updated. I get 5 more points every time I collect dots. As expected, we start on the small level, and the initial level is 0, 1. As we collect dots, the remaining dots decrease. I just got killed X times, and we can see that number of live count in the right lower corner decreases as well. Now I will try to complete that level. The next level is a medium maze. And we can see that the level is updated as well. But I kept the number of lives left. Let's see what happens when it's game over now. I just died. If I insert another coin within the 10 seconds, I should get to the same level with my live count filled up. Fantastic! Everything works as expected. But I don't know if you noticed, there's a small glitch whenever we load a new level or die. This is because the camera position isn't updated. So we're going to fix that quickly. We can pull out the function named Update Camera Position and place it at a new position. And finally, after we move our characters to their initial position, we update the camera position. Now we are definitely done. In this video, we didn't learn anything new. We just implemented stuff very specific to our game. In this section, we began by adding artificial intelligence to the enemies so they can act alive and attack Pac-Woman smartly and make the game more fun. Then we enabled Pac-Woman to collect dots and bonuses and made her detect collisions. We then unraveled the mystery of HUD or heads-up display, and last but not least, took a look at adding levels and score. That brings us to the end of this section. There you go, we've made it. Congratulations! Pat yourself on the back on completing an entire game from scratch. I'm sure you have learned a great deal about SFML on this journey.